This lesson covers an introduction to authentication services. Now, we're going to start with X.500 directory services. Directory services provide authentication services as well as authorization services for a trusted collection of what we call principals. These are users and computers and other objects that we would consider are part of our enterprise, and therefore we have some level of trust with their communications and their requests and access to our valuable resources. So that's what directory services provides. It's a collection of trusted principals that we can authenticate and then authorize to access resources in our trusted environment. And anything outside of our directory services body and implementation, we refer to it as either a realm or a domain. Those are two terms commonly used for this collection of trusted principals. Anything outside of our realm or domain is considered untrusted. And while I say that, most implementations include the ability to establish a trust to a foreign directory services realm or domain. This is implemented through Kerberos. We'll talk about that shortly. So, directory services is all about a collection of trusted objects, the principals, users, computers, and other objects. And this establishes a logical boundary and through software controls, a security boundary to isolate these trusted principals from the lesser trusted or untrusted objects outside of this directory services environment. Now, the directory services are implemented most classically in Microsoft's Active Directory domain. And in hardware, where it actually is manifested, is in a domain controller. That would be a computer that has a server class operating system installed on it, and then has the directory services support installed on that server. So these would be a Windows server of some level with the domain directory services installed on that computer. And that establishes the X.500 directory services environment. To support that Active Directory domain, we have to authenticate these clients carefully. And Kerberos is the protocol or system that we use to support this authentication of these trusted principals to one another. See, this environment might support up to perhaps 1 billion computer users, and that would require a few more than 1 billion computers. We generally assume 1 workstation per user and then a handful of servers to support the networking infrastructure for file and print services, for the directory services, for name resolution services, for remote access services, etc., etc. So we have to introduce these few billion users to these few billion servers and have them trust one another that they are part of the same trusted domain or realm. And that's where Kerberos helps us. Kerberos uses a key distribution center that, by the way, is implemented, once again, in these Microsoft domain controllers that support the Active Directory services. So Kerberos is a component that is installed on these same domain controllers. Now, Kerberos is an open standard and also is supported on Unix and Linux systems, independent of anything from Microsoft. However, in the enterprise, Microsoft's Active Directory tends to dominate the corporate world, the enterprise solution. For strong authentication and other security services, we get involved in what we call a public key infrastructure that uses digital certificates, X.509 digital certificates. This strengthens authentication and other security services such as encrypted communications channels and encrypted storage. So data in transit and data in storage can be secured using digital certificates. In addition, these digital certificates, as I said, are used to strongly authenticate endpoints. That includes the users, the computers, the servers, and perhaps even domain name services, and even routers can be configured with digital certificates. So these digital certificates are used all throughout the networking environment. And I say that they are optional, but they are becoming more and more a standard component in the enterprise environment. Now, to support remote access, which is a commonly needed service in the networking environment, and these would be perhaps users that are telecommuting into the enterprise. They might have web-based applications. They need to access data repositories on the enterprise network. They might be administrators that are managing the infrastructure systems themselves. Things along these lines. They might be wireless computers and users that are using the wireless access points. And they might also be used for authenticating a virtual private network and encrypted channel from perhaps a telecommuting user out on the internet who's connecting into the corporate environment and needs to build a VPN. These are all remote access users. And these remote access users, because they are physically not required to be in the building to connect to our network, they're coming in perhaps over the internet, over a dial-up modem, over the telephone lines, or over a wireless connection. They don't have to be physically in my building to connect into my network. I have less trust for these users, and therefore I need to strongly authenticate them, more strongly than the guy who actually has to come past my security guard, show his ID, his badge, walk through 3 locked doors, sit at a desk with a cubicle surrounded by his coworkers, and if somebody doesn't belong there, those coworkers would recognize that that's a stranger and he shouldn't be sitting at Lulu's desk, and they'll go get the security guard. Because these remote workers don't have to go through those physical access control security controls, I need to more strongly authenticate them, and that's what these next 3 bullets talk about. The first one is remote authentication, dial-in user services, or RADIUS. Now, that's the open standard for strongly authenticating, authorizing, and then auditing or accounting those users' activities. So that's the original implementation. It's an open standard called RADIUS, Remote Authentication Dial-In User Services. Now, Cisco took that open standard and implemented it in a Cisco environment and added a few extra Cisco bells and whistles and interoperability features, and they call theirs TACACS. The new version is called TACACS Plus. That's Terminal Access Controller Access Control Services. And the third version is TACACS Plus. That's a Cisco implementation of RADIUS, essentially. It has a few extra bells and whistles, but typically those are available for Cisco backend as well. It requires a Cisco environment in the backend, so it's a little more proprietary. And then finally, the new remote user authentication service is called Diameter. Now, it's a play on words. They say the second generation of RADIUS is 2 times as good as RADIUS, so 2 times R is diameter. 2 times radius equals diameter. Okay, that's where they came up with this term diameter. So diameter is the new generation of these authentication services. And diameter actually has the ability to be implemented in the new cellular 4G networks that haven't yet hit the streets. I know many of you might feel you have a 4G cell phone. There is no 4G today. This is called 4G LTE, long-term evolution. It's not true 4G and does not fully implement diameter. And so diameter is the new version of this, enhanced bells and whistles all the way around. And again, its major benefit that it brings into play is support for the 4G cellular networking environment whenever we get to that point. So this is an introduction to authentication services for networking infrastructure. We'll take a break here and pick up where we left off. Picking up where we left off, we're going to look at different authentication protocols. Now, these are placed in more historic order. Some of these early ones are no longer used, but let's look at them anyhow. We're going to start with the password authentication protocol. Even before this very first authentication protocol was introduced, there were network communications that were being established. These were typically done using acoustic couplers, which is essentially a modem. This was done over telephone lines. And in the old days, if you were a guy that had a computer, you're already a champion. And if you were a guy who had a computer and an acoustic coupler and you knew how to use it, you're a really good guy. And if you actually knew the telephone number of another computer that had an acoustic coupler, man, you must certainly be the guy. So back in the earliest days of networking, there was very little need for authentication because access to these systems was so rare, so limited. The only people that had them were the guys that had the legitimate need. They were the intended users. But as these modems got more and more popular and the average Bobo started getting access to a modem, the server side of this, the bulletin board owner, for example, realized the need to authenticate those people that were dialing in and accessing his system and tying up his system. So they introduced first the password authentication protocol. Basically, this was a username and password, but this information was transmitted over the telephone lines in clear text. So if anyone was eavesdropping on that telephone line, which was a possibility, they would clearly be able to decipher the username and password and then would be able to dial in as that user. So this, while it was the first step at authenticating those users, was very non-secure because of this clear text username and password over the wire. Shiva was a manufacturer of modems back in the early days, and they recognized this weakness. So Shiva introduced an encrypted version of password authentication protocol called Shiva's PAP or SPAP. And this used this same username and password, only it used very rudimentary encryption. So now a bad guy would have to eavesdrop on the wire and then crack the encryption. Now, if he was any good, the encryption could be cracked pretty readily. It wasn't very strong encryption. However, for those days, there weren't that many bad guys. There wasn't that much of this hardware around. And as a result, there wasn't much of a threat to the security of this encrypted username and password going over the wire. Now, a better approach to authenticating a user remotely is to avoid having to send those credentials over the wire. That way, if a bad guy is able to eavesdrop on the wire, if I don't ever send the username and password, then the bad guy can't ever steal the username and password. Well, how do you accomplish that? That's where the challenge handshake authentication protocol came into play. So this was a huge improvement over SPAP. And it avoided sending username and password over the hazardous, hostile, vulnerable remote connection. It was referred to as a zero-knowledge proof. Prove to the server that you're the right guy without ever telling the server your password. Yet you could tell him enough that wasn't your password that he knew you knew the password. And so this is called a zero-knowledge proof, and this is the open protocol, challenge handshake authentication protocol. Now, Microsoft, the premier implementer of the corporate environment MS-CHAP. So they took the open standard challenge handshake authentication protocol, put the proper spin on it, the proper bells and whistles to integrate it into the Microsoft authentication environment, into their domain environment, their implementation of their X.500 directory services environment. And they called this MS-CHAP. And then over time, they improved it. The current version is MS-CHAP version 2. So this is Microsoft's spin on the open standard of CHAP. The open standard of CHAP supported PAP, SPAP, CHAP, and basic authentication, which is clear text, similar to password authentication protocol. But once digital certificates got involved, MS-CHAP couldn't support those. They didn't want to have to rewrite the whole authentication scheme of MS-CHAP, so they added an enhancement called the Extensible Authentication Protocol. Now, what this guy does is it sits on top of MS-CHAP and is basically an application programming interface for authentication services into the MS-CHAP authentication engine. It basically supports any current authentication scheme that isn't natively supported, as long as that authentication scheme, that mechanism, whatever it is written to the EAP application programming interface, the API. So this guy now opens up the authentication mechanism to any current or any conceivable authentication scheme we come up with in the future. And I say for the foreseeable future. 1,000 years from now, it won't be necessary. But as far as we can project into the future, EAP will support these new authentication schemes. And that's what this guy does for us. It says we'll do everything MS Chat version 2 can do, and then anything that is currently written to the API and anything that we figure out in the next decade or 2 or 3 that is also written to the Extensible Authentication Protocol application programming interface. And an example of these EAP supported authentication protocols includes Cisco's proprietary lightweight EAP utilizing X.509 digital certificates. Now, that digital certificate is used first to authenticate one or both endpoints. That's the server to the client and the client to the server. It then can be used to establish an encrypted channel and SSL tunnel, secure sockets layer tunnel, between the client and the server. And then we can implement additional authentication mechanisms inside the encrypted tunnel. However, this requires more of a Cisco backend to support the lightweight EAP, since it is Cisco proprietary authentication. Microsoft does something extremely similar to lightweight EAP, LEAP, and they call it protected EAP. So this is sort of Microsoft's version of LEAP, only it requires a Microsoft backend talking to Microsoft's Active Directory on the backend. So LEAP and PEEP are two implementations of the Extensible Authentication Protocol into different authentication databases or systems, directory services. We'll take a break here and we'll pick up where we left off later. Let's continue with a look at X.500 directory services as a networking infrastructure service. Now, X.500 directory services was developed by the Telecom division, and their objective was that they recognized there was a need to authenticate and authorize endpoints or users in a large corporate networking environment. As many as 1 billion or so users and as many as 1 billion or so computers. And how would such an authentication and authorization system work with such a large number of users and computers? And in addition, recognize the space that would be required. And I'm talking about around the planet. I'm not talking about a building that would hold 1 billion users or computers, but recognize that this would be a distributed environment, perhaps even a global environment that has to be supported. That's where they came up with this model. X.500 is a standard or a protocol that is a model for how to build a network operating system to support this global networking environment. It might be utilized by large corporations, not the internet, because the internet wouldn't be a trusted environment, but this provides an element of trust for many, many users and computers. So we have to have computers, or a series of servers, if you will, that support this directory services. And these are commonly referred to as domain controllers or directory services servers. In implementation, Microsoft refers to these as domain controllers, Microsoft being the premier implementer of directory services. Today, it's about the only directory services database we use for the enterprise networking environment. Microsoft calls these domain controllers. It supports this distributed database of trusted objects and all the attributes that go along with all these trusted objects. Again, the boundary of what is trusted lives within what we call a domain or a realm, and anything outside that domain or realm is untrusted. So we have these many, many different servers now called domain controllers, again, to support this globally dispersed networking environment. And these servers have to share the same information. In other words, they have to have a common knowledge. So they require synchronization. This is also referred to as replication. So if a user in Oshkosh creates a new user or computer object and adds that to the directory database, that new object in the database, that new information, must be replicated out to all the other domain controllers. And this has to happen fairly quickly so that they all have the same information, so that the system can continue to operate without interruption. We have to have this bidirectional synchronization. We also have to be able to easily administer this environment. So we need administration access. We need to be able to group these objects logically and geographically. And this is typically done with something called organizational units. That's a logical grouping. And we also have a site, which is a physical grouping. And because we may have a different set of security concerns for the users in Oshkosh versus the users in Schenectady. And so we'll have a physical grouping called a site. However, I might have administrators in Oshkosh versus standard users in Oshkosh. And therefore, I would have different OUs to implement different security controls over the administrators, different from those controls over the users. X.500 includes a specially designed protocol called Lightweight Directory Access Protocol. And this is our tool, if you will, to support the communications between the administrators and users and the directory services database. So LDAP is the communications protocol between the various nodes in the directory services environment and the users in that directory services environment, and then the directory services servers, which are called domain controllers. That's LDAP does this. We need authentication services, and we're going to use Kerberos for this authentication service. Kerberos is covered in a different lecture. We'll be talking about that later. And we also need access control services. This is the authorization service. An administrator has more access than a user to the control panels for the different services, but that administrator doesn't need the same access to a database that the user might need. So we have different levels of authorization that are required between the different types of users in this computing environment. So we need access control services. Authorization is one of those components. And the way this commonly gets implemented is through the implementation of rights and permissions. So you can grant rights and permissions at varying levels to varying individuals or groups of individuals. In addition, we need these users to be able to connect to these directory service systems, these domain controllers, and they need to be able to identify where they are. And this is over an IP network, so we need IP connectivity. In other words, we need name resolution services. And in order to support X.500, DNS will be required because DNS has now been enhanced to include what we call service locator records, SRV records. And these SRV records are the various services that support the X.500 directory databases. The way we locate these domain controllers, if you will, are through DNS. And those domain controllers, of course, provide those directory services. And finally, X.500 supports a naming scheme such that we can have billions and billions of objects, each with a unique name, in this same trusted environment, and uses a hierarchical naming scheme, including a local host, a domain name, and a top-level domain name, TLD. And classically, these three pieces form what we call a fully qualified domain name. These three pieces then are an essential component of X.500 directory services. Typically, we will know that we're a commercial entity, that's that top-level domain, versus an educational organization like an EDU or military or government, MIL or GOV, that's your top-level domain. And then we'll have what type of commercial entity this is. What's the name of that commercial entity? In my example, we're using Boboville, a commercial entity, boboville.com. We have that domain name and top-level domain. And then finally, we have the server's name. In this case, it's web server 1, and that would be the local host name for that web server that is a member of the trusted entity domain or realm called boboville.com. So using this three-tier hierarchical namespace, I can uniquely name billions of objects. And that's a requirement for X.500 directory services. We'll knock off here for a little while and pick up with the next lesson. This lesson continues with a look at X.500 directory services. Now, X.500 directory services is a model that was introduced by ITUT, the International Telecommunications Union, Telecom Division, and it was first implemented in Banyan Vines. We're talking about late 1980s, early 1990s. Banyan Vines was the first network operating system that utilized this model as their structure, their foundation for their network operating system. Novell followed and called theirs Novell Directory Services. And finally, Microsoft came into play in the year 2000 with Windows Server 2000. Now, the Microsoft Active Directory has dominated that network operating system marketplace, and we no longer see Banyan Vines or Novell Directory Services in most environments. It's been pretty well replaced with Microsoft's Active Directory. Now, remember, this is a global distributed database with potentially billions of user objects and billions of computer objects, and then dozens or perhaps even hundreds of attributes that must be stored for each of those billion objects. We have a huge database, and it's globally distributed, and it's got bidirectional replication processes to keep those copies of that distributed database synchronized and consistent with their knowledge. Now, the tool that we use to query and access that giant database is a protocol called Lightweight Directory Access Protocol, LDAP. This is the protocol designed to reach into this giant repository of objects and attributes and allows easy access for administrators and users and the different services to communicate amongst the other domain controllers. So LDAP is used commonly within this directory services environment. LDAP uses port 389 to communicate over on the network. Now, the directory services is container-based. It's a hierarchical model or structure with a hierarchical naming space, and based on the groupings, we can apply a common administrative policy. And this administrative policy can be extremely complex and have multiple policies that combine, and some overrule other policies, things along these lines. So these are in implementation generally referred to as group policy objects. This is Microsoft's implementation, and this provides an easy platform. And I say easy, it can get extremely complex, but it is a way for administrators to apply a policy perhaps consistently globally, different policy perhaps from one location to another, different policy for one type of user versus a different type of user. And these establish boundaries and can be used to assign rights and privileges to individuals and to groups and perhaps even to services amongst themselves. A group policy is our primary administrative tool that can be implemented through the directory services interfaces. Now, as I said, the X.500 directory service is a hierarchical structure. As we see here, the triangles shown in this diagram represent the boundary of a namespace. This is also referred to as a domain or a realm. But the objects that live within each triangle are trusted and trusting of all the other objects within that triangle, within that domain, within that realm. And as we see in this diagram, I have 3 different domains, 3 different realms of trust. However, I can build an external trust between 2 of these domains or realms. And I can make it a one-way trust or a two-way trust. In other words, they trust each other with a two-way trust. In implementation, in the Microsoft environment, the two-way trust is the default. So what we see here is a root domain, and basically this domain is very often left empty with just a few administrative accounts and a few administrative computers, servers, if you will, domain controllers. But other than that, this typically remains empty, but it establishes the environment, the enterprise networking environment, directory services environment. And then we spawn a second top-level domain called a root domain. And this first top-level domain is where we might begin to start populating the domain with users and computers and other types of objects. And within that domain, I can build a hierarchical structure for organizational units. And using these different organizational units, I can group computers and users that have something in common relative to the organization. And then I can apply a group policy to that OU. So the policies can be assigned at the domain, the site, or the OU. Site being a physical location, domain is a logical boundary established by a namespace and then enforced by software controls. And then within that namespace, I can further subdivide that with the hierarchical structure of organizational units. And I can link these policies at any of these levels for a very granular level of control. But at the same time, the policy can be applied to hundreds, thousands, even millions of objects with simply linking it at one location. Now, we also see a third domain off to the right, a child domain. This implies a contiguous namespace. So if the top-level domain in this example is called sumco.lan, the child domain would have a contiguous namespace, a subset of sumco.lan, and in this example, we call it child.sumco.lan. The child domain must have this contiguous namespace, but also has the same two-way trust between its parent domain and the child domain. And the trusts in this environment, by default in implementation, are also associative. In other words, the child domain has a trust relationship with the root domain. The root domain has a trust relationship with the sumco.root domain. And as a result, there is trust between sumco.root and child.sumco.lan. So it's transitive in addition to being the two-way trust that we described. So we'll take a quick break here and we'll pick up with more networking infrastructure shortly. In this lesson, we're continuing with our analysis of X.500 directory services. Remember that this is a distributed database, potentially globally distributed database that stores hundreds, thousands, perhaps even millions, up to perhaps a few billion directory services objects. And users must be able to locate those objects. That's the whole principle behind directory services, is that we have these trusted users and these trusted resources, and the users should be able to locate these resources no matter where they exist. Physically, they exist within this directory services database, and we need to be able to locate these services, these resources, when we need them. The way we locate these resources is through the domain name system, DNS. Within DNS, we populate SRV records, service location records. And as we see in the dialog down below, inside DNS, we have mappings for Kerberos and LDAP in this one example. And we see that these are service location records. And if you look under data, you'll notice that there's a section. One of them is listed as 88. The other is listed as 389. Those are the port numbers that these services use. So Kerberos is going to use port 88 and LDAP is going to use port 389. So when a client is looking for an LDAP server, that would be a domain controller in Windows Active Directory and in implementation. When a client is looking for an LDAP server, the client will query DNS for, in this example, boboville.com, and you'll see that namespace listed over the left-hand side of this dialog. And he will look for an SRV record that uses 389, and that would be an LDAP server. If he's looking for Kerberos for authentication services, he would search the boboville.com namespace for an SRV record that points to 88. That is the port number used by Kerberos services. So DNS is used to locate these X.500 directory services. Continuing on, we're going to look at Kerberos. Now, Kerberos is the authentication system that is used commonly within directory services. So Kerberos provides authentication services, does not provide authorization services. I hear it commonly misstated that Kerberos provides some form of authorization. It does not. Kerberos provides only authentication services between principals in a directory services environment, the trusted realm or domain. Now in Kerberos specifically, they refer to this as a realm. That's the trusted body of principals. Principals are users in computers and other objects that exist within this common namespace, this common realm. So Kerberos uses a third-party component called the key distribution server as the trusted component in the environment. And if the key distribution server authenticates a principal to another principal, because we trust the KDC, each principal can trust that they are actually communicating with the appropriate other trusted principal. So we have a user, for example, and we have a resource server, for example, two principals in a Kerberos realm. Now, these two objects, users and resource servers, will have accounts on the KDC, on the key distribution server, and also this KDC is implemented on a Windows domain controller in implementation in the Active Directory environment. And so these two objects will exist within this domain controller's database. And if the user can authenticate, then the KDC trusts that that user is who he claims to be. His identity is now authenticated. And when a server boots up, it also authenticates to the KDC. And now that resource server has been authenticated by the KDC. So if the user wants to talk to the resource server, he goes and checks with the KDC, and the KDC validates the identity of the resource server, and now the user trusts that he's communicating with the appropriate resource server. And vice versa. When the client actually initiates communications with the resource server validates the user's identity through the KDC, and if the KDC says, yep, that's really that user, then the resource server trusts that that user has been authenticated. And that's where Kerberos stops. Kerberos does not perform authorization. Now, in order to support all these services that we just walked through, we have the key distribution server, may also be called the key distribution center, the KDC. It also runs the authentication service. That's the initial logon for each of these principals. And in order to maintain this authenticated credential, the KDC produces something called tickets. It uses a great deal of encryption, in this case, symmetric key encryption, to store securely the information on these tickets. The authenticated credentials for each of the principals are stored on these tickets in an encrypted manner. The KDC produces this ticket and also adds a timestamp to it so that the ticket couldn't be stolen, cracked, modified, re-encrypted, and then used again by a bad guy. The ticket has a timestamp to provide anti-replay protection. If the timestamp has expired, typically the timestamp is good for 5 minutes on a client accessing a resource. Typically that ticket is good for 5 minutes. And that's not enough time for an attacker to steal a ticket, crack the encryption, modify the ticket to say what the bad guy wants it to say, re-encrypt it, and then replay the ticket to the resource server. Okay, this has been a review of some of the services that are provided by the X.500 directory services and an introduction to Kerberos, the authentication protocol used by directory services. We'll take a break here and we'll pick up shortly. Let's continue our look at Kerberos, the authentication protocol used by directory services. Kerberos is named Kerberos because it's based on the 3 heads. Kerberos, of course, is the mythological creature that had 3 heads, and it was a dog that guarded the gates of hell. And in this case, the 3 heads of the authentication protocol include the KDC, that's the Key Distribution Center, in implementation, that is a domain controller in Windows Active Directory. The second head is the principal, the authenticated user, that's the consumer of resources. And the third head is the principal that is the resource itself. In this case, we're talking about, for example, a file and printer sharing service. So these would be the 3 heads that are represented by Kerberos. The KDC is the trusted component. That's the source of the trust. And it establishes this security boundary, this realm, of trusted principals. Those are users and resources, or primarily the nature of the principals we're interested in. A user will authenticate to the KDC and then is trusted by the KDC. The resource server on boot up authenticates to the KDC and then is trusted by the KDC. They are issued Kerberos tickets, and the Kerberos ticket has two halves. The ticket includes proof of authentication as defined by the KDC. So the KDC builds this ticket and he validates the authentication of the user and then encrypts that validation in half the ticket. And in the other half of the ticket, he encrypts the authentication of the other principal. And in this example, we're talking about the file and printer sharing service on that resource server over to the right. And when the user then wants to access that resource server, he uses this Kerberos ticket, feeds it over to the resource server. The resource server validates that the ticket actually came from a trusted KDC, and then goes and decrypts the side of the ticket that includes the user's credentials as defined by the KDC. And now the resource server trusts that the user's identity has been validated by the KDC. And if the KDC believes this is that user, the resource server trusts that it is also that user. At the same time, the principal, when it receives the Kerberos ticket, says that if the KDC trusts that that's really our trusted resource server, then the user also has trust that he's communicating with the right resource server. And so based on this level of trust for the KDC and the two halves of the Kerberos ticket, the principals now authenticate to each other and have trust that they're communicating with the appropriate other endpoint for this access to the resources. So Kerberos is referred to as a single sign-on technology. Again, the point is of single sign-on is that the user needs to authenticate one time, the time that he logs on to the Kerberos KDC, and at that point he's given a getting ticket. Using that as his access token, he now can use that getting ticket to access any resource enterprise-wide for the duration of that ticket. Typically, this TGT, as it's called, a ticket getting ticket or a ticket granting ticket, this TGT is good for about 10 hours by default. That would be about the time of a workday, a typical workday. You get in a few minutes early, you work an 8-hour day, you take an hour for lunch, you work a few minutes late, you're at about 10 hours. So that's the single sign-on component of Kerberos, is that we log on once to the KDC, we get our TGT, and using that TGT, we are now able to authenticate to any other resource enterprise-wide. And what is this enterprise-wide? Well, that is the basis called the realm. That's the boundary that defines trusted objects. Anything within the realm with the same namespace, like boboville.com, is trusted by and trusting of every other object with that same namespace. First, we have this logical namespace that defines this logical boundary of trust. But then in implementation, we use software controls to limit access based on that namespace or that level of trust. So the realm is this boundary defined by namespace, but implemented and enforced by software. And again, we talked about the common namespace. It is a domain and a top-level domain affiliation. And then each object, each principal will have additional namespace, perhaps by the OU, and additionally username and or local host name, for example. Objects, again, within this realm can trust and be trusted by other objects within the realm. Between realms, you can build trusts to extend this trusted environment. So we use external trust between these realms or domains, as Microsoft calls them, and we can extend the trusted environment, the trusted computing environment. Now we're looking at remote access services that also are commonly incorporated in this directory services environment, because very often we have telecommuting users. Very often we have administrators that don't want to have to go to the other building or fly across the country to modify the configuration of some server. And we also have wireless users that also run through this same remote access user configuration or implementation. And because these users don't have to physically be within the building and physically connect to wires that are only available inside the building, we don't have as much trust for who those people are. So we therefore will more strongly authenticate those remote users. And that's where radius, TACACS, and diameter come into play. Radius is remote authentication, dial-in user services. That's the open standard. Cisco took that open standard of radius and implemented it in a Cisco environment. They call this TACACS, or Terminal Access Controller, Access Control Services. And the new generation of these remote access services is diameter. This is the latest and greatest. And again, diameter comes to us as a play on words. It's the second generation of radius. It's twice as good as radius. So 2 times radius equals diameter is the notion as to where they came up with this name. Now, these authentication services are referred to as AAA services. They include authentication, authorization, and accounting. But today, we don't need the accounting part of it. Today, we need auditing or accountability. So we do logging of the actions that these users who have authenticated and have been authorized are performing. What exactly did that guy do? I want a record of it, just in case there was something bad or some mistake occurred. And again, this is all an extension of the original point-to-point protocol, a dial-up service protocol used originally by telephone and modems attached to our computers. And originally, we were dialing up bulletin boards. So we'd have a client with an acoustic coupler over a telephone line to a bulletin board that was another server with an acoustic coupler. And again, this point-to-point protocol, this dial-in service, extends to wireless and VPN services and will soon be used in the cellular environment in the 4G networks. We'll take a quick break here and we'll pick up where we left off. Continuing our lessons on remote access services, we're going to look at diameter. Diameter is the newest generation of these AAA services. Remember, AAA is authentication, authorization, and originally it was accounting. But today, more so, it's auditing or accountability, keeping track of what the user has done. But diameter is the new kid on the block, and it's the next generation of radius. They get the name playfully from diameter being twice as good as radius. 2 times radius equals diameter. The diameter protocol is that same AAA service, but it has improvements in many, many categories, many areas of the AAA support that radius and TACACS provided. However, the primary area of support is aiming at 4G cellular. Now, today, many of us have cell phones that imply that they are 4G capable. The kicker is there isn't any such thing as 4G today. There's 4G long-term evolution, LTE. That is a tiny step, perhaps not even 10% of the way between 3G and true 4G cellular. True 4G cellular has many requirements that our cellular systems today cannot support. So true 4G does not exist today. It's 4G LTE. Diameter is one of the protocols that is going to be used to support the services that true 4G is going to require on our cell phones. Now, one of the primary issues with 4G is that your cellular connection and your data flow connection will be as good as if you were attached using a hard wire to a network. In other words, you always will be able to get a signal and you will always have a high data rate of connectivity using that signal. Now, what we know is with your cell phone today, you will always find dead spots here and there throughout the local community, and especially as you travel to more remote locations, you get worse and worse connectivity. In other words, you might not get a signal, and if you do get a signal, you're going to get very slow data throughput because the connection is really weak. Well, that's not satisfactory with 4G cellular. One of the techniques they're going to implement with 4G cellular is that on your cell phone, no matter who you pay as your cellular carrier, and today those carriers include AT&T and Verizon and others along these lines, those are the carriers. No matter who you pay, all the carriers must support your connection. So if, let's say, you're an AT&T customer with your cell phone, that's who you pay your bill to, and in the diagram here on the slide, we're going to say that cellular carrier A, the blue tower, is AT&T. So while you're close to that blue tower, you're going to get a good strong signal and you're going to get a good data rate when we get to 4G. However, as you move from the area around the blue tower to the area around the red tower labeled cellular carrier B, that would be the competition of AT&T, like Verizon, for example. As you move away from carrier A towards carrier B, your signal is going to degrade from carrier A. However, when the signal from a carrier that you don't pay any money to, when that signal gets stronger than your carrier A signal, carrier B has to carry your connection, in spite of the fact that they're not being paid by you in any way, shape, or form. And this is one of the components of 4G cellular that has yet to be ironed out. However, this is the area where Diameter, a protocol that will support transferring your connection from your carrier when you're near the blue guy, as you move towards the carrier B away from the blue guy, Diameter will transfer your authentication information, your credentials, from carrier A to carrier B so that carrier B can continue to support you with the strongest signal that you have available to your cell phone, in spite of the fact that it isn't even the carrier you pay. That's a pretty amazing thing, and I don't know exactly when this is going to sort itself out. That's why we're not at 4G yet. But when we do get to 4G and we get those agreements ironed out between the different carriers, that no matter who you pay, the carrier that provides you the strongest signal must carry your connection. When we get to the point where that detail is ironed out, we have the protocol to transfer your credentials from carrier A to carrier B and maintain that connection and that high data rate, maintain your session with whatever your services are, whatever you're accessing, whether it's internet, whether it's local resources on your corporate enterprise network, et cetera, but the Diameter protocol will keep your credentials and your sessions intact as you transfer from one carrier to another. So this is a review of the remote access protocol Diameter, also called a AAA service, and Diameter is the new generation that is replacing Radius and TACACS. We'll take a break here and we'll pick up with the next lesson. Picking up where we left off, we're going to look at a diagram that shows the implementation of Radius and TACACS. These implementations are very similar. One is the open standard Radius, the other is the implementation of Radius by Cisco. So Radius and TACACS are approximately the same service. Now, in this example, we have a user on the lower left. And that user is using some sort of remote connection. And that remote connection started out in the old days as dial-in over analog telephone lines. But today, these services using the point-to-point protocol has been extended to virtual private networks and to wireless systems, wireless network connectivity. So that remote user could be one of those three types of users connecting into the corporate networking environment. And they would connect into the network access server, and this is the guy that he might be a VPN concentrator, he might be an old Radius server that has the modems attached to it with telephone lines, or this might be a series of access points that are managed by a wireless access controller. And that would be the nature of this network access server, depending on the nature of the clients that this environment is supporting. In most cases, this remote user would establish the connection to the NAS server, network access server, and that network access server would allow communications only for the purpose of authentication. Any other request would be denied. If you notice, there is the switch between the NAS server and the resources on the LAN, and that switch is currently open, because until that client authenticates, that's the only thing the client can use this system for, authentication. So the client would connect up to the NAS server. The NAS server would prompt the client for authentication. And that authentication might be based on the Radius server or the TACAC server. That's that middle server on the top there. And that system typically will support its own independent user database, or that system might backend into a directory services database for authentication services. If we're in that corporate environment, we have directory services. Let's use that bigger database. It may simplify some of our needs. However, if I don't want all my users to be able to dial in, maybe I just want a smaller database, more isolated, more localized, if you will. In that case, I'll use that local user database on the Radius server itself. So that backend there behind the NAS server for authentication could be one or more servers that provide that authentication service. Now, if the user successfully authenticates, the authentication server notifies the network access server that this guy is now authenticated and he's allowed to do these things. And at that point, the network access server closes that switch. By the way, this is a logical switch in this example. I've diagrammed it here physically, but it is a logical switch there. And only when the user is authenticated and authorized to access resources on the LAN would the NAS server allow that user to make the connection into the resource servers. And so that's what this guy does. Moving on, we'll take a look at virtual private networks. Now, this is one of those supported remote access services, VPNs. Basically, what the VPN typically does is isolate the communications that are flowing through the VPN from the network that the VPN or that this communications are flowing through. So we have some form of isolation, encapsulation, that make these communications virtually private because of this isolation from the networking environment that these communications are flowing through. Most of the time, the VPN implies an encrypted channel because very often what we're trying to accomplish with this isolation is to keep the information confidential. The best way we have to keep information confidential as it flows across a network is by encrypting all the information. So typically a VPN implies that we are encrypting all this information so that it is non-readable in case somebody's sniffing those wires and able to capture that packet, if you will. And if we encrypt it, it makes it unreadable. That's our primary implementation. However, VPN does not exactly mean encryption. We have other forms of isolation. I might encapsulate a layer 3 protocol in a layer 2 frame so that I can send that IP packet through ATM network or frame relay, for example. And so this is also a form of VPN. These are the two ways that we see VPNs used, either encapsulation and not encrypted or encrypted. We see a list of VPN technologies on the side. We see Secure Shell. That was one of the earliest implementations of a secure channel. Now, it originally was not designed as a VPN. It wasn't really for, let's say, file transfers, for example, or the flow of sensitive data. It was really designed for securing the remote administration of servers. It replaced Telnet. Telnet was one of the early protocols used on IP networks so that an administrator could remote access into a server and reconfigure that server as necessary without having to get up and sit at the keyboard and a monitor in front of that server. So he could do it from his workstation using Telnet instead of having to walk down the hallway and sitting in front of the server. The problem with Telnet, though, is everything is in plain text. So if there is any bad guy in the environment who might be capturing the information flow across that network, the bad guy could actually steal that information and perhaps even use that information to reconfigure the server himself in an unauthorized fashion. So they figured out that Telnet was non-secure. Let's encrypt those communications because this is kind of sensitive information. So they invented Secure Shell as an encrypted channel for remote administration. That was its primary use. Today it's evolving into more of a VPN. We have the point-to-point tunneling protocol, PPTP. Now, this was produced as a joint venture between Microsoft and Cisco. And this guy originally used RC4, the encryption algorithm, to encrypt the payload. So Secure Shell was an asymmetric algorithm. Point-to-point tunneling protocol used RC4, which is a symmetric key encryption algorithm. These two guys encrypted data as it flowed across the network. L2TP is an encapsulating protocol but does not provide encryption. So there's no confidentiality services with layer 2 tunneling protocol. L2TP is another Cisco proprietary technology, but is also now being used by Microsoft. IPsec, because the Internet Protocol has no security services built in, if you needed to run security services over an IP network, IPsec, IP security is your primary tool. This guy encrypts information over IP networks and is a classic and probably the most heavily utilized VPN technology today. Now, the next one down, SSL, Secure Sockets Layer, is a little bit different from a VPN. See, a VPN implies we have known and trusted endpoints, like within the Kerberos realm, whereas SSL says I can be used in an environment where the users are essentially anonymous, but I can still secure the communications channel. So SSL is used heavily on the public internet, where we have anonymous users that are accessing resources up on servers, and without having to know who that user is, we can implement a secure channel, SSL channel, and encrypt all the information that flows back and forth. So that's where SSL came from. However, it is being used today more and more as a VPN technology. And that extends to the newer version of SSL called TLS, the Transport Layer Security. So TSL is an enhancement, if you will, to SSL. Finally, the implementation of SSL as a VPN, it is now being implemented as Secure Sockets Tunneling Protocol, SSTP. So these are all VPN technologies that either encrypt or encapsulate without encryption the information flowing from one node to another node on a network. We'll stop here and pick up where we left off. This lesson covers network address translation, called NAT, and its close relative, port address translation, PAT. Now, NAT was invented, NAT and PAT, by the way, jointly, were invented to extend the lifetime of IP version 4. IP version 4 uses a 32-bit IP address, with a handful of those addresses allocated to the public address space used on the internet. Problem is, those public addresses were consumed very quickly, and we started to run out of public IP addresses. So NAT and PAT were invented to help extend the lifetime of IPv4 by sharing one or more public IP addresses amongst perhaps hundreds or even thousands of users on the public internet. So instead of needing hundreds or thousands of public IP addresses, they all can share one or two public IP addresses, minimizing the need for so many public IP addresses and extending the availability of those public IP addresses. Now, NAT and PAT are typically configured on the external firewall. This would be the firewall that isolates your privately owned enterprise network from the public internet. Firewall, of course, is a security device that provides isolation as a security boundary between these networks of differing trust levels. We have more trusted environment behind the firewall on the private side, and less trust for that network environment outside on the public side of that firewall. So NAT is configured on that external firewall where we have this boundary between public and private. And again, it's all about sharing these public IP addresses, making them much more usable and much more shareable. In addition to this extension of life for IPv4 and the more efficient use of the public addresses that IPv4 supports, NAT and PAT also help to hide the internal IP address structure from the public internet. Many bad guys operate and exist on the public internet, and I don't want them to have any vision at all on my private network, because the more they can identify or footprint or map out what my network infrastructure looks like behind that firewall, the more readily they can attack and target inside that firewall. So I don't want them to have any vision whatsoever. I'd like that to be a black hole. Well, that's one of the things that Nat and Pat help me do, is the bad guys on the public internet that might be able to capture packets, called sniffing on the public internet. They'll only be able to identify public addresses because Nat replaces private addresses with public addresses. And as a result, on the public internet, the only thing the bad guys will ever see are public addresses. And he has then no vision as to where is my DNS server on my private network? Where are my other servers? Where are my clients? What is the IP address architecture like in my environment? And so I hide all this from the public internet. So that's one of the benefits of using NAT and PAT on that external firewall as we've described. And some people talk about NAT and PAT as if they're two completely different things. And there is enough difference where they are different. That's why they have two different names. But at the same time, if I plan to implement NAT, I can't really do it effectively unless I also use PAT. So consider that if you have NAT, you're also running PAT. They operate like Siamese twins. You simply cannot separate them if you need the functionality, full-blown functionality that they support. So what we can use NAT and PAT for is use one public IP address and share that one address amongst dozens or hundreds or even perhaps a few thousand users on the private network. Many clients can share one IP address, public IP address, for use on the public internet for browsing purposes. We also can use something called port forwarding. Again, this is a combination of NAT and PAT, where I can use one public IP address, and using port numbers, I can steer an inbound packet to port 25 to a private IP address inside that hosts my email services. An inbound packet to port 80, I can use NAT and PAT to steer that to the web server on my private network. An inbound port 443 to my web server that's running SSL. An inbound port 21, map that to the server that's running my FTP server on my private network. So this is called port forwarding for inbound services, providing public services to the internet where the request is anonymous. And then on the next one, we have a one-to-one mapping. So suppose I have an application server that is stateful. In other words, it has to maintain session state for each client that is using the application. Typically what they do there is the application server will live on the DMZ, and you have these telecommuters that live out on the internet using public addresses. They will connect to your firewall using a public IP address, but to the one port for the application server. This would be the primary port for the application server. Let's pick a number of 20,000. So inbound to port 20,000 on a public IP address. And that will connect to that application server. But once the user authenticates on that application server, the application server will redirect them and say, the next time you communicate with me, you use port 31,200. And that way I'll know it's you, Bobo. And that way I can track your session and identify where you are in the process in my application. Maintain stateful information about your session. So the application server will now redirect each client from the authentication port to the session port for each individual session so that it can maintain different session state data for each connection. So in this case, I'll need to do a one-to-one mapping. I'll take one public IP address and map it to the IP address on the private side for the application server. And now it doesn't matter what port number it is inbound. All those inbounds to this one public IP address gets mapped to the one server, the application server, on the private IP address space. So this has been a look at network address translation NAT and its very close relative, perhaps even Siamese twin, port address translation PAT. We'll take a break here and we'll pick up where we left off. Let's continue with a look at Bastion Host systems. Now, a Bastion Host system may also be referred to as a hardened system. In other words, it has its defenses strengthened to defend itself better, isolate itself better from the bad guys that are attacking the server. Basically, we will implement the Bastion Host system on any computer or appliance that is publicly exposed. That would be your firewalls, DMZ or perimeter network, any system that has high-value applications or high-value data that it might be working on or holding. So any of these systems would be your Bastion Host systems. Typically, our goal is to reduce the attack surface of that computer. In other words, take away the angles that the bad guy might use to attack you. Reduce the vulnerabilities of that system to as low a level as we possibly can because of its high value or its high exposure. I want to reduce that attack vector, that attack surface, and minimize the opportunity for the bad guy to be able to break in. How do we do this? Well, it starts with, usually we'll make these systems dedicated to one or perhaps two services maximum. I don't want to take a system that's publicly exposed and put 19 different services on it, because each service is implemented in software, and that software has vulnerabilities, it has bugs, opportunities for the bad guy to break things, to break in, to compromise the system. So I make it dedicated purpose, one or two services only, like it'll run web services and maybe DNS services. But even that is probably not likely. Probably I'd make that two boxes, two separate computer servers, one for web services and one for DNS services. The fewer number of services, the fewer amount of software running, the fewer vulnerabilities. And if a bad guy does decide he's going to target this box, he's going to break in, he only gets one service. If you put 9 different services on one box and he breaks into one of those 9 services, he now can compromise all 9 services. But if you only have one service on the box and he breaks into that service, he gets the one service and he has to break into 8 more boxes in the previous example. So dedicated purpose, only 1 or 2 services provided. These systems will be patched very, very often. Now, we typically will patch all of our systems very often. We're going to pay particular attention to these boxes because those patches, those updates that we get from the vendors for the operating system, for the applications, and maybe even for the firmware on those systems, those come out regularly, and I want to be sure that these boxes get patched in a timely manner as quickly as possible. These would be your first ones to be patched after testing and approval, and these would also be the ones that I would verify that the patch has been applied and applied successfully. Next, I'll minimize the users on the box, especially those with a high level of privilege. So use the fewest number of users possible, bare minimum number to sustain the box, and also minimize the permissions, the privilege level. They call this the principle of least privilege. I will be especially diligent applying the principle of least privilege on these boxes. We talked about reducing the number of services, disable or uninstall any unnecessary services. Don't just think about what I need it to do, so I'm going to install the DNS service. I'm now going to look at that box as it installed, and I'm going to remove many of the services or applications that got installed automatically. I don't need them on this box. Kill them. Get them off the box, because any software that's running increases the attack surface. If you don't need it to be running, stop it. Get it off the box. We talked about deleting unnecessary software. Always add a personal firewall to these boxes. Today, most systems include a personal firewall. Be sure the personal firewall on these Bastion Host systems is installed and active and configured correctly. Next, I'll install antivirus, anti-spyware, anti-malware, whatever you want to call it, all these defenses against malicious software. And of course, those types of protections require regular updates, and they typically will implement routine scans. So be sure you are very often updating those signatures of the malware, and that you are very often performing as full a scan as you can afford to run. I might run host intrusion prevention system on these boxes as well. In other words, look for a series of packets that form an attack. Look for malicious behavior on this system. If a process is assembling an executable file and installing it as a service, man, this is a bad thing. This is a danger Will Robinson. This is red flags should be waving. So we want a host intrusion prevention system installed on these boxes as well, very much like the antivirus. Another tool that is commonly used on these Bastion host systems is an external vulnerability scan. This is a system that is not the Bastion host, but some secondary system that we point at the Bastion host system and have this system interrogate that box to see what a bad guy would see and look for the vulnerabilities that a bad guy is looking for. So externally, I'll run a vulnerability scanner on my Bastion host system to identify the vulnerabilities that a bad guy might be able to identify. And finally, I might implement operating system integrity verification. Now, this is done more and more. It's still relatively new, but there's a new piece of hardware that's being installed on many enterprise level systems called a Trusted Platform Module chip, a TPM chip. And this TPM chip can actually take fingerprints of your critical core operating system files and other configuration parameters. And on boot up, it will go verify the integrity of that file and that configuration. And if it finds any problems, any deviations from what it knew as its trusted boot up state, the system will simply fail to boot up. And we might also run these integrity verification procedures on the system while it's running. In other words, I knew that I configured this guy to point to the DNS server at 10.10.10.5, and if its DNS server is pointing anywhere other than 10.10.10.5, notify an administrator immediately. Someone has altered the configuration, and this would be an attack vector. So again, these are many of the things that we will do to establish what we call the Bastion host system, also called a hardened system. And again, any system that is high value, either processor data or is publicly exposed in a high risk environment, we want to harden those boxes, make them Bastion hosts. These are many of the things that we will do to strengthen the security of these machines. We'll knock off here for now, and we'll pick up shortly where we left off. In this lesson on our networking infrastructure series, we're going to be looking at the endpoint systems. Now, these are the client-side systems that are attaching to our enterprise network environment, and we're going to look at how we might secure those devices. So let's start with a summary of what are these devices. Well, they start with the desktop computer, and that would include laptop computers. These are the workstations that our users are going to be spending the bulk of their day on. But today we're getting more and more of these bring your own device type devices, like pad devices and handheld devices. Cell phones even would fall into this category in some instances. Now, what this says is we're starting to lose control over the operating systems and the configuration of these devices that are attached to our enterprise network. Typically, it had been just desktop computers with the occasional laptop. Now we're seeing a pretty good split of those two between desktop and laptop computers, and we're adding to it cell phones, pad devices, and other handheld type of computing devices. So we have a great deal more opportunity for non-secure configurations, for bad software, malicious software that might find its way onto our corporate network, things along these lines. And so we have heightened concern these days over these endpoint systems. Now, these endpoint systems need different forms of administration. I don't want to have to walk to 4,000 computers and reconfigure some IP address or some firewall setting. I want to be able to do this from some remote location with some centralized tool like a policy. And so here we need remote access for administrators to be able to get to these boxes, to reconfigure them as appropriate, but not have to go to that box physically. So that's remote access and for the purposes of remote administration. And then remote administration en masse is typically deployed by a policy, usually through directory services. And I can apply policy based on organizational group, on domain, on site, as well as several other options. But depending on the type of systems that you're using for deployment of these policies, you may have a great deal of flexibility and be able to identify different types of handheld devices, like different types of cell phones, different types of pad devices, because each pad device requires its own software and its own specialized configuration with its own specialized vulnerabilities and security concerns. Now, something else that we can do from an administrative standpoint is deploy desktops from a centralized location. Now we would use something like a thin client at each workstation, at each cubicle, if you will, that has no real intelligence, no real operating system of its own, like we would think of an operating system, Linux or Windows, for example. It would just have enough of an operating system to boot up, connect over the network to the virtual platform, and then that platform would feed down a desktop. And basically, it's like the image of a desktop, the screen capture from a desktop for this user session. And now I only have to manage and maintain that image file that I'm pushing out my desktop image to all these thin clients. I only have to maintain that one copy rather than maintain 4,000 copies, because each client is going to get their own copy of that one image. So it simplifies my administration if I can use the virtual desktop. Now, this is referred to as platform as a service, part of a cloud function. Now we're getting into cloud services, and platform as a service means I'm going to push down your operating system from my virtual environment, from my cloud environment. I don't have to push down the entire desktop. Perhaps you have your own desktop, and I can provide you access to a specific application virtually without installing that application on your computer. In other words, I have one copy of, let's say, Microsoft Office that I'll install and maintain on my virtual servers. And then when you want to run Office, you'll double-click an icon that I've put on your desktop, but that connects up to my copy of the application, and you actually run Word from my server, not from your workstation. This says I don't have to patch 4,000 copies of Microsoft Office. I patch one copy, and I can keep it very well maintained. I don't have to worry about some client out there who hasn't been doing his patching, and as a result, we have increased vulnerability on that system. Now, very often, I'll want to harden these boxes, these endpoint system, client systems, as much as I possibly can, and still provide the required functionality. Service is always balanced against the required functionality for that box. So what I'll do is I will see to it that we have regular patching implemented for all these different types of endpoint systems. I will harden them to the best of my ability. That means I'll install a minimum level of software in order for you, the worker, to do the work you have to do, but not much more than that bare minimum. I will assign permissions following the principle of least privilege. If you don't need to be an administrator to run your workstation, I'm going to keep you as a standard user. If you don't need full control over those files, I'm going to give you read-only control over those files, for example. Just the bare minimum of privilege. I'm going to install a host-based intrusion detection or intrusion prevention system, perhaps, and this helps to identify malicious behavior, aberrant behavior, suspicious behavior on a system, and might quarantine those processes and protect me from some sort of compromise. From an administrative standpoint, I can write policies that say these are the things you're allowed to do with the computer and these are things you're not allowed to do with the computer. And then I'm going to teach you about those acceptable use policies through awareness training, and I'm going to make you sign an agreement that says, yes, I understand the things I'm allowed to do and the things I'm not allowed to do with your computer. And that combination of acceptable use policies and awareness training provide me the justification to enforce my policies when they are violated. In other words, I can now reprimand, I can now punish if there is a breach of our policy. On these endpoint systems, I almost always will include antivirus, anti-spyware software, and I'll perform regular updates and regular scans. I'll install a minimum level of services, and I'll disable anything or actually uninstall or remove software for services that I don't need that endpoint to perform. I'll implement a minimum number of user accounts on that workstation. I'll install a personal firewall and be sure it's enabled and configured and updated. And I'll implement some form of configuration management. In other words, I'll isolate the user from any of the configuration dialogues that he shouldn't get to, and I may actually go verify the integrity of configuration parameters. And if I find that they've been altered, now I will go reprimand and I'll figure out how did this get changed, and I'll punish whoever it is that caused the change. By the way, it may not be the end user's fault that a configuration detail has gotten changed. It might have been an indication of a compromise or a breach, and this is something I'd want to know as quickly as possible. So this has been a review of the endpoint systems and how we might secure them in an enterprise networking environment. We'll take a pause here and we will continue in just a few minutes. In this lesson, we're going to look at virtual machines. Now, virtualization has been a really hot topic lately. This is a very fast-growing and very rapidly deployed technology in the enterprise. Virtual machine takes a single piece of hardware called the bare metal. That would be the actual physical PC, like a server class machine, and it would then have an operating system installed on it. Now, it might be Linux-based, it might be Windows-based, something along these lines. So that's the standard computer that we would install. And then on that computer, we might install various applications. As we see in the diagram, we have the bare metal down at the bottom, then the host operating system as the next layer up, and off to the left, we see several applications that we can run on that standard computer. And that's a fine thing. However, virtualization requires another layer at the application layer called the hypervisor. Now, what this hypervisor does is it simulates the resources of a computer and supports the installation of a guest operating system as an independent virtual machine. So that guest operating system needs a CPU. Well, the hypervisor says, here's your CPU, I have your CPU. The hypervisor doesn't have a CPU. It will actually commute that call for CPU down to the actual physical bare metal hardware through the operating system and use the physical CPU of that real physical box. The guest operating system has no clue it's actually in a virtual environment, that the hypervisor is pretending to be all those physical resources when actually he's just the middleman who says, yes, here's your printer port, hand me your rendered print job, and then the hypervisor will turn around and hand that print job down to the host operating system where the real printer port is attached. The hypervisor simulates these physical resources to the guest operating system. Then on that guest operating system, I can install multiple applications or services as needed. And as we see here in the diagram, we show 3 different virtual machines, each running different series of applications. This is great for increasing the utility of your hardware. Many systems operate at 10 to 20% utility. In other words, you're wasting 80% of your computer because you're only using it for a single desktop and a single series of applications for that one session. So if we install the hypervisor and virtual machines, those machines now will have their operating systems and applications and sessions that are running, and we are now more fully utilizing that physical hardware, the CPU, the RAM, the hard drive space, and then other resources that we might attach to that system, and providing those resources of availability to the guest operating systems as well to the local host operating system. So we are greatly optimizing system capacity. I can reduce the amount of hardware that I have to buy as well. Instead of having to buy, in this example on the diagram, I would need 4 different pieces of hardware. Well, that's a lot of cost, and that's a lot of space, and that's a lot of electricity. I can do all this on one piece of hardware, reducing that cost, that space, that electricity, that heat dissipation problem. I can use the virtual machines to isolate processes. Suppose the virtual machine number 1 has top secret data and processes operating on it. Well, then I can use the virtual machine 2 for secret data and processes, and virtual machine 3 for confidential applications and data. And you see how I can use the virtual machine as the boundary to isolate these different levels of sensitivity or trust or value. And I can isolate these processes for these various reasons. Perhaps they're different cost centers. So I have VM1 for one cost center, VM2 for a different cost center. And I can track the usage and then bill those cost centers accordingly for their consumption of my resources. It also supports a high availability and easy disaster recovery, because the virtual machine now lives solely in software. and I can actually clone that software, take a snapshot of it. And if this particular virtual machine gets corrupted, I can simply point that virtual machine over to the copy, fire up the copy, and I can be back in business in a matter of seconds instead of perhaps a day or two to repair the hardware, reinstall the operating system, reinstall all the applications, restore data from the backup. I can take that snapshot in just a few minutes and I can restore it in just a few seconds in many cases. So it's great for high availability needs and easy disaster recovery. In addition, I can easily scale up my number of virtual machines by simply cloning them. I need another DNS server. I need another DHCP server. I simply copy the files that are the virtual machine and boom, suddenly I have a brand new virtual machine. It also supports the use of different operating systems on one hypervisor. So I've got a great deal of flexibility. Suppose I need 4 Windows servers and 8 Linux servers. I can do that on one piece of hardware using a hypervisor. This is the way most data centers are going today, and this is the way most cloud systems are implemented, through the use of a big piece of hardware with a hypervisor and then many guest operating systems or virtual machines. Continuing on, we're going to look at the different levels of service that these virtual machines provide. We have infrastructure as a service, where our virtual machine is operating more as a network infrastructure appliance. Remember, these infrastructure systems are very often going to be Bastion Host type hardened systems and dedicated services like routers, firewalls, and other infrastructure services. So I can implement my infrastructure in a virtual environment, again, for easy recoverability, disaster recovery, things along these lines, scalability, etc. Next, we use platform as a service that allows me to configure a series, one or more database servers like SQL Server, for example, and clone it in a virtual environment to improve scalability and disaster recovery and capacity. Application servers, web servers, etc. This is a platform as a service. Now, in addition, platform as a service, depending on whose definition you're looking at, may include virtual desktops that are spawned down to client workstations or client thin clients, dumb terminals. So that virtual desktops that we see software as a service might also be considered platform as a service, depending on whose definition you're looking at. So don't be surprised if you see that guy fall into one of those two categories. Then software as a service is the virtual desktop, virtual applications that we spawn. In other words, I have one copy of your graphics editing software that I maintain, and I don't have to install it on the 300 workstations out there. I only have to maintain the one copy. When you want to launch that application, you double-click an icon on your desktop. That reaches across the network, and I feed you your application over the network without ever having to install it on your machine. So I have to maintain one copy of the application, not 400 copies. Now, these virtual machines are commonly used for cloud environments, for HoneyNet, which is used as a defensive and learning tool in a corporate environment, mostly a highly sophisticated environment. HoneyNets aren't all that common, but basically it's an attack environment to draw the bad guys over there to the HoneyNet and away from the real resources. We use virtual machines for our testing and quality assurance labs to be sure that our applications are working as we expected, that the client side of it is connecting properly, that the patches we apply don't break other services or applications. Now, the hypervisors are being provided by many different companies today. One of them is VMware, one of them is Microsoft's Hyper-V. Oracle produces something called the VirtualBox, and there are many other hypervisors that are available. Some of them you have to pay for, some of them are free, and you'll need to make that decision based on your budget and your needs and what your policies will allow. So this has been a lesson on virtual machines. We'll stop here and we'll pick up later. Continuing on with our lesson on networking infrastructure, we're going to take a quick look at mainframe computers. What is a mainframe? Basically, this was used primarily in the day where the computer occupied an entire room. One machine consumed a whole room, and it was the sole source of computing power and storage and anything related to the actual processing of data. This is the one place where we had a real computer. but we couldn't get all the users in that one room because the computer pretty much occupied it, and we didn't want that many people bumping around on this one very expensive system. So what we would do is install thin clients, also called dumb terminals, wherever we needed them. And they could be in the same building, in the adjacent room, or perhaps across WAN links or other remote access connections. So we could distribute them wherever we needed these thin clients, and then provide a connection path from the thin client to the mainframe itself. And this allowed many, many users to actually access the mainframe and get their work done, input their data and retrieve their result back from the mainframe. So the thin client was not an actual computer. It really had no CPU of its own. And basically it was just enough of a machine that would allow the system to boot up into some fundamental rudimentary operating system. It would install a network stack and a network interface card driver so that we had connectivity back to the mainframe. And it had a keyboard and a monitor, but it didn't have any local storage and it didn't have its own internal CPU. It basically was a window that connected the user to the mainframe. And then keystrokes would go up the stream to the mainframe, and the mainframe would send either characters back or might send screenshots back to the client computer, the thin client. No processing was done on the thin client. All the work was done back on the mainframe. Now, the way the mainframe would access these clients or give each of these clients a turn is through a polling process. See, the only intelligence in this network environment was in the CPU. However, we might have 100 or 1,000 or more users that periodically would need to access the CPU. So in order to give everybody an opportunity to use the mainframe, the CPU itself, the mainframe itself, would reach out to each client one after one after one and say, do you have something to say? No, you do? Okay, transmit, transmit, transmit. I'll start working on that. I'll come back to you in a little while. Go to the next guy, go to the next guy. So through a polling process, the mainframe would query each client and see if that client had something to send upstream to the mainframe computer. This is a terribly inefficient way to share the utility of that mainframe, but there was only one device that had any intelligence to make a decision about whose turn it was to transmit or receive data. So that's how it was managed. Now, the mainframe would have a series of applications installed, but those applications would only be installed during the boot up process in a phase called the initial program load, the IPL. So if a bad guy were going to steal computer time, the bad guy would need to get his program listed on the initial program load script, and then the application would be available for his use and access. And again, this was often done to steal computer time because these systems would hire out time windows to various clients. Well, if you didn't want to pay for it, you wanted to steal it, your program listed on the IPL, and then you'd have to get that initial program load to install. Well, that thing only fired off during boot up. Anytime that the mainframe rebooted, which triggered the initial program load script, that was the time where the bad guy could inject his program that was stealing computer time. Now, these boot ups or IPLs were scheduled because we'd schedule the downtime of the mainframe, and that way it was predictable. You wouldn't be in the middle of some big processing job and we're suddenly going to shut down the box to perform some maintenance or repair. And as a result, the IPLs, the boot up, was scheduled. If a reboot occurred in an unscheduled fashion, this was a cause for red flags. What the heck just happened? That wasn't supposed to boot up right now. And is somebody trying to steal computer time by getting their data, their program loaded during the IPL, the unscheduled IPL? So this was the major threat to the mainframe computers. With this, we'll take a break here and we'll pick up where we left off. In this series of lessons, we're going to be looking into wireless networking. Wireless networking is one of the most rapidly growing areas of network communications. It's simple and inexpensive to assemble, to modify, to disassemble and relocate and reassemble a wireless network. Wireless networking is cheap and easy because it doesn't require a wired infrastructure like Ethernet does. In Ethernet networking, before you could establish the network communications, you'd have to run all sorts of Ethernet cables throughout the building, and this was costly and time-consuming and presented an investment in that specific facility. In wireless networking, you have a very inexpensive wireless access point, and only the access points need a back-end wired infrastructure to connect into the corporate network, the resources, and perhaps even the internet. So the wired infrastructure is substantially reduced when it comes to a wireless network. One of the early issues with wireless networking is that the bandwidth was low. Originally, the bandwidth was at 2 megabits and then moved to 11 megabits, then 54 megabits, and today we're approaching hundreds of megabits and even gigabits in our wireless networking. So the throughput is growing rapidly. It's a wonderful thing. However, because wireless networking is nothing but emanations, these are electromagnetic waves propagating through the air, bad guys can intercept those radio frequency communications and can steal your data. So there still is an increased security concern. Also, the bad guy doesn't need to be within your facility to attach to your wireless network, like he had to in the early days of wired networking, Ethernet. He literally had to plug his cable into your infrastructure back in those days. With wireless networking, he can be across the street or down the block, or a bad guy with a good antenna can even be miles away and still connect to your wireless network. So there are still substantial security concerns, and we'll be addressing those later in this series of lessons. Now, the wireless network typically relies on two primary components: the wireless access point, which provides the infrastructure for the wireless network. This is typically attached to the wired infrastructure that hosts the corporate resources, the servers and other communications. And then the other side of this is the client side. And typically this is simply a wireless network interface card that is very inexpensive these days. And we'll call this the wireless NIC. Now, we have different scales or sizes of wireless networks. The first one is the personal area network. Personal area network typically is considered to be about a 10-meter radius. This is about 33 feet. And so this personal area network is typically going to operate using Bluetooth or perhaps even something called Zigbee, which is a super low power wireless communications mechanism. So that's for personal area network, about 10 meters radius. The next size network we're going to look at is the local area network. Now, this includes a large family of IEEE 802.11 specifications, and this would be the 802.11b, G, A, N, and AC. Now, those last two, 802.11n and 802.11ac, are the newer multiple input, multiple output technologies that are getting us great distances and fantastic data rates. And then finally, we have the metropolitan area network and the wide area network using wireless communications. And again, here we'll use that MIMO, that multiple input, multiple output technology. A similar but competing technology is called WiMAX. And then also our 4G cellular networks as they evolve. We're still not quite at 4G cellular in the true sense. As 4G cellular evolves, we'll be utilizing that 4G cellular network for metropolitan area networks and wide area network communications. Now, this is the IEEE 802.11 series of specifications. These are the primary ones. There are others, but these are the primary ones that we need to be familiar with for wireless networking. The original specification was 802.11, as I said, provides about 2 megabits of throughput, data throughput, and it operated at 2.4 gigahertz. 802.11b, still in the 2.4 gigahertz frequency range, added a new technology called direct sequence spread spectrum and got us up to about 11 megabits. Then both the 802.11a and G added something called orthogonal frequency division multiplexing, This got us to a much higher data rate of 54 megabits. Now, the primary difference between A and G are that the 802.11g specification still operates in that 2.4 gigahertz frequency range, but the 802.11a operates at 5 gigahertz. This is a more isolated frequency spectrum, and there's not so much interference in that 5 gigahertz frequency range. The kicker, though, is you need specifically 802.11a access points or transmitters and receivers and 802.11a wireless network interface cards with all the clients in order to get that 802.11a network running. Now, the next standard down is 802.11i. With the original 802.11, they implemented Wired Equivalent Privacy, WEP. Now, that was the security component of 802.11, the original wireless specification. 802.11i is the repair or the replacement for that failed, very vulnerable Wired Equivalent Privacy in WEP. The 802.11i is the specification. However, in implementation, the vendors produce something called Wi-Fi Protected Access and Wi-Fi Protected Access version 2, WPA and WPA2. These are the repair components for the security flaws in Wired Equivalent Privacy, the original security component for wireless networks. Now, as we said, 802.11n and 802.11ac are the new guys on the block. These guys use multiple transmitters and multiple receivers and multiple antenna to increase the data rates, upwards of hundreds of megabits, perhaps even approaching gigabits of throughput. And not just 100 meters or so, these go hundreds of meters and perhaps even miles or even tens of miles as this further develops. So watch for these MIMO 802.11n and 802.11ac technologies to evolve, and they're evolving rapidly. These are coming into the commercial world as we speak. And then finally, I'll mention these bottom two, 802.11h and 802.11j. As we implemented wireless networking standards here in the United States, we bumped into some conflicting standards in other countries and nations, and as a result, there were some frequency conflicts that had to be resolved. And these last two, H and J, are specialized projects, work task groups by the IEEE trying to resolve these frequency conflicts. We'll take a break here at this point, and we'll pick up with more wireless network engineering. Continuing with our lessons on wireless networks, let's nail down a few terms, a few definitions. The first term we're going to look at is called the cell. The cell is the collection of wireless clients that are associated, and also the wireless access point if there is a wireless access point present. So these have a communications session established between themselves, and that collection of nodes, wireless nodes, are considered the cell. Now, we have two different structures, if you will, for the wireless cell. The first one is called an ad hoc network. And this would be the collection of wireless clients without a wireless access point. They associate to one another and form their own cell without any sort of centralized controller or moderation. And the administrative tasks of maintaining the cell, the communication sessions amongst themselves, is traded off from one node to another over time, so that each node eventually shares some of the burden, the responsibility, if you will, for maintaining the communication sessions. Now, if we add the wireless access point to this environment, we now have something called an infrastructure wireless network. And this is the way most of our wireless networks operate. This would be where we have perhaps a hotspot, like at the Starbucks coffee shop, and that includes the wireless access point that has a wired connection. This is an Ethernet connection, typically to the internet, and that would be the example of this hotspot. And then, of course, the clients, the customers that go into this coffee shop would associate to that wireless access point and form the cell at this hotspot. And in the corporate environment, more the enterprise environment, the Ethernet connection to the access point or access points would plug into the wired infrastructure for the enterprise. This would be the collection of servers, file servers, print servers, application servers, etc., the network resources that the workers in the enterprise need to access over time. So the clients then would associate with that access point and then would be given connectivity to the networked resources, the wired resources in the enterprise. Now let's learn a couple more terms. These are the signaling schemes that have been used historically. The first one was introduced in 802.11, and it's called Frequency Hopping Spread Spectrum. And this allowed one data stream. In other words, it was kind of like a baseband network, only one data stream to carry your data. This was used in, as I said, the early 802.11 specification gave us 1 to 2 megabits of throughput. And this is also the technology that is used by Bluetooth. Bluetooth networks still today use frequency hopping spread spectrum. The next step up is called direct sequence spread spectrum. This still provides only one data stream, but allowed our data throughput to increase to about 11 megabits. So it's a little more efficient on its communications. So that got us to 802.11b is where we were first introduced to DSSS. Now, 802.11g and 802.11a use orthogonal frequency division multiplexing, OFDM. And that increased the number of data streams from 1 up to 48 data streams. And this allows us that huge jump in throughput from the 11 megabits at 802.11b to 54 megabits that we see with 802.11a and 802.11g. And now the latest family of wireless networking uses multiple input, multiple output, called MIMO. And basically this allows us the use of several transmitters and simultaneously several receivers, and then of course each transmitter and receiver has to be attached to an antenna. So we have multiple antenna as well. Now this takes the orthogonal frequency division multiplexing and multiplies it by 2 or 3 or 4 or all the way up to 8 transmitters and 8 receivers and 8 antenna in the new draft specification 802.11ac. Another area of technology that we need to understand are the frequency ranges that we operate within using our wireless networking. Now, here in the United States, our Federal Communications Commission, the FCC, administers and allocates the frequency spectrum. There are 2 frequency ranges that the FCC has allocated for wireless communications, such as wireless networking here in the United States. Now, while this is definitely a U.S.-centric body, this Federal Communications Commission, recognize that other countries have their own equivalent of our FCC that is responsible for the frequency allocation in their countries. And they don't always agree. They don't always line up. We do have a couple of problems where we've allocated frequency spectrum to wireless networking here in the US, and the devices that are manufactured here, when we take them to Japan or to Europe, for example, interfere with their frequency allocations. They might use it for satellite communications or for emergency broadcast communications, things along these lines. So there have been a few wrinkles that we've had to sort out relative to these frequency spectrums. But let's look at these 2 specifically. The first one is called the Industrial, Scientific, and Medical Frequency Band, the ISM band, and it operates in a range of 2.4 gigahertz to 2.5 gigahertz. Now, that's the local area network frequency band, and it was used in 802.11, 802.11b, and 802.11g. So those 3 standards all operate in this 2.4 gigahertz frequency range, the ISM frequency range. However, so do microwave ovens, so do wireless telephones in the home, so do many other research components. In other words, there's a lot of interference, there's a lot of traffic in this frequency range, and as a result, you might have poor communications, poor network throughput because of the interference in this 2.4 to 2.5 gigahertz frequency spectrum. So because of its crowdedness, sometimes we have problems or diminished throughput. So to solve this problem, the FCC had also allocated the region between 5 and 6 gigahertz, called the unlicensed National Information Interchange Frequency Band, or the UNI band. There isn't much happening in this frequency range. This was really intended for nothing but wireless networking. And as a result, it's very uncrowded. The kicker, though, is you need different radios, different transmit and receive radios to operate in this 5 gigahertz frequency range. Now, this was defined by 802.11a that requires the 5 gigahertz radios. Let's also discuss quickly the 802.11n and 802.11ac standards. The 802.11n would be at least the G frequency range at 2.4 gigahertz, multiple transmitters, multiple receivers, multiple antenna, but may also include the A radios as well. So the N by itself doesn't exactly specify whether it's the 2.4 gigahertz or the 5 gigahertz. This is something you're going to have to carefully look at in your specifications for the devices you're interested in. However, the 802.11ac is focusing more heavily on the 5 gigahertz frequency range because it is going to use up to 8 transmitters and 8 receivers and 8 antenna. They have the opportunity now to isolate into this very non-crowded frequency spectrum. We'll take a break at this point and pick up with more wireless networking. Continuing with our lessons on wireless networking, let's take a look at the security that was first introduced with our 802.11 original wireless networking standard. Because wireless communications are nothing but emanations, in other words, all of your data is being broadcast into the air using electromagnetic radio frequency signals, it's very easy for a bad guy, an attacker, to pick up these radio frequency signals and perhaps steal your data, or perhaps use their knowledge that they learn from the communications they're stealing to break into the wired network behind the access points. In other words, now accessing the corporate network with the valuable resources. So even with the original 802.11, this vulnerability in wireless networks was understood, and they introduced some security called Wired Equivalent Privacy, or WEP. And the notion was make the wireless network at least as private, secure, as the wired network. So that was the goal of WEP. Now the kicker was WEP was developed by radio frequency engineers, the IEEE, and they weren't exactly the right guys for implementation of this strong authentication and strong encryption for the wireless networks. WEP was fraught with vulnerabilities and flaws. Now, WEP supported the use of a pre-shared key. In other words, authentication was based on a password. Or you could turn off this authentication process, and it was called open authentication, which means that we will accept anybody's request to associate with the access point. In other words, you don't even need to know the password. So it also then used encryption for the data communication. Once you were authenticated, it would use a RC4 symmetric key stream cipher for encrypting your data stream and providing confidentiality services. In other words, the bad guy only sees ciphertext, and that doesn't make any sense to him, and he doesn't know how to decrypt that ciphertext. So he can't understand the communications. While he's able to capture them, they're all encrypted, and he can't read it. Another security component that WEP supported was called MAC address filtering. The MAC address, of course, is a layer 2 address that is hard encoded into the wireless network interface card. In other words, each wireless NIC has its own globally unique address. And if you are the administrator for the access point, then you can build a list called a whitelist of the MAC addresses that are authorized on your network. And only those MAC addresses will be allowed to associate with the access point. There are problems with this all over the place. First, everybody used the same password. Everybody in the cell knew the same password and used that same password not just for authentication, but that password was the encryption key for the data flow. And that meant that anybody who knew the password could decrypt your communications. So we don't have a one-to-one secure channel. The cell is kind of secure. But then the kicker was the password was too short. It was too easy to crack. So a bad guy using a special cracking tool called WebCrack could steal the password, reveal the password in just a matter of seconds. And as a result of revealing the password, not only could he associate with the access point and gain access to the wired infrastructure back behind, he could also use that same password to decrypt all of your communications. So this was extremely weak stuff. In addition, it was the access point that said, hey, user, what's the password? And the user would provide the password. So the client is authenticated, but the client never was able to authenticate the access point. Is this really the correct access point? You see, a bad guy can stand up his own wireless access point, give it the same SSID, and spoof the legitimate wireless access point for the enterprise. So the legitimate client can't tell whether or not he's associating with the true access point for the enterprise or whether it's a rogue access point that some bad guy set up because there was no way to validate the identity of that access point. And it's easy to set up a rogue access point. Now that we understand we've all got this same common password and it's got vulnerabilities and it's easy for the bad guy to crack it, one of the things you would do is you would rotate that password, change that password regularly to make the bad guy crack it again and crack it again and crack it again as you rotate the key from one to the next to the next. Well, the problem is it was very difficult to coordinate everybody in the cell to change their key. There was no automatic way to do this. If you change the password on the access point, you'd have to now communicate out with all those users of the cell and give them that new password. And how do you do that now that you've changed the password on the access point? So maybe before you change the password on Monday, we're all going to use this new password. Boom, you have to send it out to 200 people. And the problem is when you send out the same password to that many people, a bad guy can steal a copy of the message one way or another, and boom, he's right back in. So there was no easy way to change those passwords and encryption keys. Because of all these understood vulnerabilities, a new standard was developed called 802.11i that was the replacement for WEP, and it improved the security from WEP to a more acceptable standard. So we'll take a break at this point and we'll pick up with Wi-Fi Protected Access, the 802.11i series. This lesson is going to continue our analysis of wireless networking. We're going to start with a discussion of how do clients connect to the wireless network. In most cases, this is through an access point, a wireless access point that establishes what we call infrastructure mode wireless networking. So the access point is the moderator for the cell, and it negotiates and manages all the communications that are occurring within the cell. That would be the access point itself and all the client nodes that are associated with the access point. So the access point is configured with what we call a service set identifier. Now that is the name of the wireless network. And it might be something like Starbucks Hotspot 27, for example. That would be an example of a name of an SSID. And a client computer then, wireless node, would scan the airwaves and identify these service set identifiers that are broadcast by default 10 times a second by every access point. And that's the default configuration. This can be turned off, and there might be some security reasons to do that. But if we're looking at a hotspot, we're kind of advertising our wireless connectivity, and we want clients to find us and associate with us. However, in a corporate environment, we might want to turn off this SSID broadcast to try and hide ourselves from the bad guys. And mostly we're knocking down the dumb bad guys, because a good bad guy can find your SSID even if you've turned off the broadcast. So basically, we're knocking down the dummies here if we turn off that SSID broadcast. However, by default, the access point will broadcast its SSID 10 times per second, and then a client will choose that SSID because that's the network he wants to associate with. If we have, let's say, 2 or 10 or 100 access points, we can configure them all with the same SSID and establish what we call a roaming environment for the wireless network. In other words, we're extending the physical boundaries of the wireless network. Now remember, by default, a wireless cell can extend up to about 100 meters before the signal degrades too much and we have a hard time communicating with the access point. So consider that we have a 100-meter radius around the access point, and suppose I wanted to run 200 meters or 300 meters or 400, I simply stage these access points at the proper distances from one another, and I give them each the same SSID. And now, as a client who has chosen this Starbucks SSID, as he roams across this distance of several hundred meters now, his client node will identify that we're getting a stronger signal now from access point number 2 with the same SSID. So the client node will disassociate itself from the first access point and reassociate with the second access point, which will maintain his client association, his session, if you will, with the wireless network. So the client node will automatically reassociate with the SSID that it had chosen that is providing the strongest signal as he moves from one physical location near access point 1 to a different physical location nearer access point 2 that's now providing him the stronger signal. So as a client now attempts to connect to the wireless network and utilize the resources of that network, the client will request authentication and association with the access point. And only after a client is authenticated and associated, that's when the client can now utilize the resources of the wireless network. And as we had said, wireless networking is inherently insecure because of its emanations. The wireless network is nothing but emanations, and emanations are the communications itself, the packets, the payloads that carry the data across the network. They're being propagated into the air. Well, what this says is that a bad guy 10 meters away or 100 meters away, or even a bad guy with a really good antenna could be perhaps even miles away and still steal this data that is propagated through these emanations. So we have to implement a stronger security for wireless networks than all other networks, all other things being equal, because of this emanations security issue. As we said in prior lessons, the initial security for wireless networks was called Wired Equivalent Privacy, or WEP. And WEP was poorly designed and had way too many vulnerabilities and faults. So the IEEE initiated a second task group called IEEE 802.11i, and their goal was to repair wireless security to an acceptable state. And they came up with this 802.11i standard, and then the vendors took that standard and began to implement it in their actual products. And this is where we come up with what we call Wi-Fi Protected Access, WPA, and Wi-Fi Protected Access version 2. Now, WPA, the initial phase of this improved security for wireless networks, was designed to be nothing more than a firmware update for the original 802.11 hardware. The vendors didn't want to have to force the users of wireless networks to immediately go purchase new wireless gear. So the intent was design this first level of upgrade to where it's nothing more than a firmware upgrade that their older gear would support. In other words, just throw away WEP from that same gear and install WPA on that same gear, and it should work. And this improved security to a reasonable level. However, it still wasn't as good as what we wanted, so it was a transition phase. Basically, at some point, we expect you to buy new hardware, wireless network users, and that's where WPA2 comes in. Because of the higher security demands, we have higher computational demands, and as a result, we needed more powerful wireless networking gear. So it basically required that the users of the wireless network would throw away their old gear and would have to purchase new wireless gear like access points and wireless network interface cards. So WPA2, the second version, is what we should all be using today. As of 2006, all Wi-Fi Alliance certified gear must support WPA2. And so anything you bought in the last 8 to 10 years will probably be WPA2 compatible, and that's what you should be using because it has the higher level of security. Now, WPA2 is also referred to as Robust Secure Network, or RSN. So WPA, WPA2, and RSN are the implementations of the standard that is 802.11i. And 802.11i included the requirements to satisfy a personal home use level of security that is using nothing but a pre-shared key, in essence a password. And then for the enterprise level, the corporate level networking infrastructure, it required some back-end services like Radius, remote authentication, dial-in user services that is used to help with authentication, authorization, and accounting. And it also then required a user database with a list of authorized users for this wireless network. That infrastructure could also include the directory services defined by X.500 and is commonly implemented in what we call Microsoft's Active Directory. But that's more of a commercial grade or enterprise level of security, and most of our home users don't have the sophistication resources to implement that type of infrastructure. So they watered it down and said, okay, we'll also use just a password if you're using this type of technology in your home. And again, the notion is get off of WEP, and today you should also be off of WPA, and you should be running only WPA2 for the strongest level of wireless security. We'll take a break at this point and pick up where we left off shortly. Continuing with our lessons in wireless security, we're going to quickly review 802.11i and then move forward. 802.11i was the replacement for the flawed security called Wired Equivalent Privacy, or WEP. There was an initial phase called WPA, Wi-Fi Protected Access, that was supposed to be nothing more than a firmware upgrade for that older 802.11 hardware. Eventually, the expectation was that you would have to replace that older hardware with new hardware that was more powerful and supported the stronger WPA2 Wi-Fi Protected Access version 2, and it's also called the Robust Secure Network. Again, the initial phase, WPA, was a transition phase that should have ended somewhere around 2006 to 2008, and we should all be running WPA2 today. Now, what is this Wi-Fi thing? What are we talking about? This is called the Wireless Fidelity Alliance. This is an alliance of the vendors, the manufacturers that produce wireless networking hardware. And the kicker was there was the standard from IEEE called 802.11 that was basically the definition of specifications. And then it was up to the vendors to interpret those specifications and build hardware that satisfied those specifications. And in the early days of wireless networking, each vendor was off doing their own thing with their own special bells and whistles, and none of the hardware was interoperable with other vendors' hardware. So the Wi-Fi Alliance came together. The vendors agreed, listen, we need to all be consistent so that if you buy a Cisco access point, you can use a Netgear wireless network interface card and vice versa. And they should still interoperate fully with all the specifications satisfied. So that's what the Wi-Fi Alliance is all about. It's the vendors of the gear, and the alliance is designed to be sure that all the gear they produce, while it still may have those proprietary bells and whistles, it still is 100% satisfying the specs and interoperable with the other Wi-Fi Alliance certified gear. And the Wi-Fi Alliance read the spec called 802.11i for advanced security in wireless networks, and then introduced WPA and WPA2 to satisfy those heightened security needs. And as a reminder, we had both the personal authentication and security and the enterprise authentication and security, and the personal for home use that simply relied on a password for authentication, whereas the enterprise level requires more infrastructure like a Radius server and some back-end user database for authentication, authorization, and the accounting/auditing functions. Now, again, as we said, WPA should no longer be in use. It uses something called the Temporal Key Integrity Protocol, or TKIP. Now, TKIP utilized the original 802.11 encryption algorithm called RC4, asymmetric key stream cipher, and it satisfies one of the problems in this regard in that it provides for easy key rotation and automatic key rotation. If you recall, in WEP, the keys were static, and there was no easy way to rotate those keys or change those passwords. TKIP satisfies that problem with automatic key rotation. In addition, it uses message integrity code to validate that the communications haven't been corrupted or tampered with. It uses a unique key pair called pairwise keys, so that each discrete user has his own secure channel with the access point, and no other user can decrypt his content. So it's just a two-key relationship. The access point holds one encryption/decryption key. The individual user holds his own. A second user would have a different key pair with the access point. A third user would have a different key pair with the access point. So each user has his own secure channel with the access point. However, because there are a lot of broadcasts that all the nodes need to be able to understand, there also is a group-wise key pair for broadcasts. So if the access point or a node was going to send out a broadcast, it would encrypt it using the group-wise key, and then everybody in the cell associated with the same SSID and access point would be able to decrypt that broadcast. However, if the client is sending a file to some file server on the back end, the wireless channel between the wireless client and the wireless access point, this not being a broadcast, would use the pairwise encryption key, and none of the other nodes would be able to decrypt that communication. That's WPA and TKIP specifically. Now, WPA also included the Extensible Authentication Protocol, which supports the use of digital certificates and potentially other authentication mechanisms. The important one for us here in wireless is the X.509 digital certificates used in a public key infrastructure. So EAP was added to the authentication scheme for WPA to support the use of these digital certificates for both authentication and strong encryption. And it also supports the use of 802.1x port-based authentication. That says the access point will allow anybody to communicate with the backend systems for authentication purposes only. But only after you get authenticated will the access point allow those clients to communicate with the network with data communications. So authentication communications for anybody and everybody, and only after you're successfully authenticated will the access point allow communications for data flow. That's some good, strong improvements over WEP. Now, the WPA2, also called the Robust Secure Network, or RSN, improves upon this tremendously. Remember, this required a hardware upgrade. In other words, throw away your old access points, throw away your old wireless network interface cards, and you have to replace them with new gear, because the computational demands of the Advanced Encryption Standard, that's the AES, are heavier than that for RC4, the original encryption algorithm. And as a result, we needed beefier hardware. So throw away your old hardware and buy new hardware. Now you can do WPA2. And as of 2006, all the Wi-Fi certified gear supports WPA2. So WPA2 is where we should all be operating today, and it includes the use of the Advanced Encryption Standard. This is currently the NIST recommendation for protecting confidential information. As a matter of fact, AES has been approved for use with secret and top secret sensitive content. In addition, WPA2 includes the use of CBC-MAC, that's Cipher Block Chaining Message Authentication Code, for integrity validation of the data to prove that the communications haven't been either corrupted or tampered with willfully by some bad guy. It also includes the use of the Extensible Authentication Protocol, as was WPA, and also the use of 802.1x port-based authentication that supports all users, no matter who they are, can communicate to the authentication system for the purposes of authentication, but only after successful authentication will any user be allowed to access data and allow data flow over the wireless network. We'll pause now and we'll pick up shortly. In this lesson, we're going to review the 802.11i enterprise level of security for wireless networks. As we see in the diagram on the left-hand side, we have the client wireless computer, and in the model, this is referred to as the supplicant. So the client is called the supplicant. Now, at this point, the client is a wireless client but hasn't yet authenticated or associated with the access point. And we're going to talk through this whole process. So at this point, the supplicant is going to identify an SSID for an access point nearby, and he is going to request authentication and association of the wireless access point. That is referred to as the authenticator. So the access point is called the authenticator because he moderates the cell. He's responsible for negotiating this authentication with the client. Now, the authenticator, or the access point, is going to use 802.1x port-based authentication back to the authentication system for the enterprise. And any client is allowed to use the wireless network for the attempted authentication process. But only those that are authenticated are allowed to actually flow data over the wireless network. So as you notice, behind that wireless access point off to the right, we see two paths. One goes up towards the extensible authentication protocol, and the other one goes to sort of a switch. Now, this is a logical switch, not so much a mechanical switch as it's diagrammed here. Consider that's a logical switch, and that functions within the access point that supports 802.1x port-based authentication. So the supplicant wirelessly communicates with the authenticator, the access point, and says, hey, I'd like to authenticate and associate. The access point reaches back to the radius server behind the firewall. This is part of your infrastructure for the enterprise. And that radius server says, well, hand him my digital certificate. Now, this is an X.509 digital certificate, a component of a public key infrastructure. And that certificate provides strong authentication and the functionality of strong confidentiality or encryption services. So the radius server, which could be a TACAX server or today could also be a diameter server, that radius server sends that digital certificate over the wire back to the access point. Now the access point transmits that digital certificate over to the supplicant in a wireless fashion. And if a bad guy is able to sniff that or steal that, that's no threat. That's no problem. If the bad guy would like a certificate, we'll give him his own copy because he can do me no harm just by having my certificate. Basically, he can prove my identity, and that's about it. And that's no harm to me. So we hand the certificate over to the supplicant, who at that point will validate the certificate. There's probably 10 or 15 validation tests for the certificate. And once the supplicant is comfortable that the certificate is true and just and valid and actually represents the network that he's trying to associate with, the supplicant will generate two symmetric session keys and pull the public key off the digital certificate. Now it takes that public key from the digital certificate and encrypts one copy of the symmetric session key. Now, it's only the radius server who has the associated private key for that public key encryption. So if the public key encrypts it, only the private key can decrypt it, and only the radius server holds that private key. So it's the only system in the entire world that could decrypt this symmetric session key that the supplicant just created. Now, the supplicant sends that encrypted copy of the symmetric session key back through the wireless network to the access point. If a bad guy steals that key, it doesn't matter because it's encrypted and the bad guy can't decrypt it. So the encrypted symmetric session key is transmitted wirelessly to the access point. The access point puts it on the Ethernet wire up through the EAP over to the radius server, who uses his private key and decrypts the symmetric session key. What we have just accomplished is now the supplicant has a copy of a symmetric session key, and the radius server has another copy of that same exact symmetric session key. And now we've established what we call an SSL tunnel. Now, when the client is transmitting anything to the radius server, he's going to encrypt it with his key, and the radius server can decrypt it with his key. So everything from the supplicant to the radius server is encrypted using these symmetric session keys. The radius server, now that he has the SSL channel established with the supplicant, that's over the wireless and the wired connection between those two, challenges the supplicant for some form of authentication. What authentication mechanisms do you support? We support this as well, whatever they negotiate upon. So over this encrypted SSL tunnel, the supplicant and the radius server negotiate authentication mechanisms. And once they choose, in this example, we're using X.509, implemented in Microsoft's Active Directory. The supplicant says, well, I'm a Microsoft client, and the radius server says, great, we've got a Microsoft database back here, we'll get you authenticated that way. And now through the SSL tunnel, they'll run through the MS-CHAP, Microsoft Challenge Handshake Authentication Protocol version 2, and authenticate the client, the supplicant, through the SSL tunnel. Now, once that client gets successfully authenticated, Active Directory notifies the radius server, yes, his authentication is valid. This is his username. These are the groups he's a member of. And the radius server will define the security policy called the Remote Access Service Policy for that client. and will notify the access point of the conditions of this supplicant's particular session. And if the supplicant violates any of these session parameters, the access point is to disassociate that client. In other words, he just misbehaved, kill his connection. So using this RAS policy, we can strongly control what the user does. And if the user doesn't do everything that the policy requires, the authenticator will simply disallow his communications any further. What types of rules can we have? We can have what is his username, what is his group affiliation, what time of day, what day of week, what protocols is he using? Is he encrypting everything through a VPN? We'll talk about that in a few moments. So far, there is no VPN. We'll also require perhaps how long he's allowed to be on the wire, how long he is allowed to be idle, and then we're going to cut him off just because he's wasting our time, et cetera, et cetera. So there are 20, 30, 50, 80 rules that we can impose on that client's session. And if any one of those rules are violated, disconnect that client. Now that Radius server notifies the access point what these rules are and says he is now authenticated. So the access point will now close that switch that we talked about. This is the 802.1x port-based authentication. We'll close that switch and will allow that client to communicate with the LAN-based resources, actually flowing data back and forth between the client and the resources and the client. However, before we allow that client to do any of that, the access point and the client will negotiate either WPA or WPA2. Hopefully today it's all WPA2. And they will establish a secure connection over the wireless component of the connection. In other words, from the supplicant to the authenticator, we're going to encrypt all this with the advanced encryption standard with CBC MAC and counter mode protocol. And that channel where the lightning bolt is shown there is going to be encrypted. However, the wire behind the access point at this moment is not going to be encrypted yet. Unless our policy set by the Radius server, unless the policy requires a VPN, the client could now communicate where it's clear text on that Ethernet cable behind the access point. At this point, we no longer need that SSL channel between the client and the Radius server. The authentication system and process has already completed. Destroy the SSL tunnel and throw away those symmetric session keys for authentication purposes. However, we've now regenerated a new key pair for the secure communications between the supplicant and the authenticator. And now, if the Radius server required it in his policy, or if the client simply chooses to do so, what should occur is the client should make his first data packet a request for a VPN through the access point, through that switch that is now closed, through the firewall, and to a VPN concentrator or VPN server of some form. And now the wire behind the access point has been encrypted as well. And we have actually two layers of encryption in the wireless section. We have the AES for WPA2, and we also now have the VPN that the client has established with the VPN server. This is how an enterprise-level wireless network should be configured. And this is one example. There are variations to this, but this is kind of a classic, basic implementation of 802.11i, WPA or WPA2 in the enterprise. We'll knock off here and we'll pick up with more wireless networking. This lesson will cover some attacks on wireless networks. Let's first look at this first term called war driving. This is where a potential attacker, potential bad guy, sets up usually a laptop computer with a wireless network interface card and some form of GPS so that the laptop is geographically located properly on a map. And a bad guy would then either walk or drive through an area and fire up a war driving application. Kismet is one, for example. It's a Linux-based utility that will sync up this GPS, and it will simply sense all the wireless access points that it can identify. Anything that is broadcasting an SSID, its beacon, if you will, the application for war driving will record that SSID and all other network parameters it can identify, and then place a marker on the map where that access point was located. And so a bad guy will simply drive around town on a sunny afternoon and be mapping out all these wireless access points. Now, he doesn't have to pay any attention. This is all automatic once he's got the right pieces in place. And then later, he'll go back to someplace comfortable for him, and he will simply poke around on the map and identify juicy targets. So this was a way of identifying where do I want to break in, and it'll identify the low-hanging fruit, the very non-secure wireless networks and the juicy wireless networks where while there might be security, the value might be very high and it might be worth some effort. So war driving is simply a map where these access points are and as many details as can be gleaned from just a simple anonymous survey of the terrain. This has been pretty well accomplished all throughout the United States and then some, perhaps globally, if you will. And it's published on a website called Wiggle, W-I-G-L-E, if I recall correctly. If you nose around for this, you can identify all the access points in a certain area based on the latest war driving analysis. The next one down is called war chalking. Once we identify the parameters for somebody else's network, if it's an easy target or something along these lines, I might spray paint some details on their building, on the wall, or the sidewalk, or the curb, so that when I'm in this neighborhood the next time, I know an easy network to get into to get me some free internet connectivity, for example. This is sort of a cryptic marking that we're going to put on the wall or the building that identifies these network parameters, because I don't necessarily want everybody to understand what I'm communicating. I don't want the victim to know that we've been able to identify the nature of his network and details about how to connect into it. So very often there are symbols that the bad guys, if you will, have defined and now commonly used to mark these details about the wireless network for easy access to this network in an unauthorized fashion. The next one is referred to as WEP cracking. Now, if you recall, WEP was the original security called Wired Equivalent Privacy for the 802.11 network. However, it was horribly flawed, and as a result, it can be cracked in just a matter of seconds. And breaking into a WEP network is referred to as WEP cracking. And there's a tool called WEP Crack that allows you to do this. Now, because wireless communications are radio frequency waves, electromagnetic waves that are transmitted into the air, anybody with a receiver can sense those waves. And we simply can eavesdrop on the wireless network. This is referred to as sniffing. And if the network isn't using encryption, then it's all clear text and it's all free and easy for me to read. And even if it is encrypted, I might start to attack that encryption and be able to decrypt packets and be able to steal their sensitive data. Now, defeat the authentication scheme. Let's say I figure out the authentication password for a network. This very often will allow me, the bad guy, to break into and gain access to the wired infrastructure behind the access point. And very often this isn't just a connection straight out to the internet. There will be servers with files and other resources that are available, and I can gain access to that wired network. Now, the last two on this list, we're going to move to the next slide and talk about them, called a rogue access point and man in the middle. So moving forward, let's look at the next slide. And we'll see a diagram that's going to show this rogue access point. That's this access point right in the center of the screen down towards the bottom. He's the attacker. And this is going to be to implement a man-in-the-middle attack. So here's the way this works. The bad guy simply acquires an access point. Now, access points are dirt cheap. You can buy an access point for $10, $20 on the internet. And it is as legitimate an access point as the enterprise-level access point that your corporation might have spent $200 or $500 for. And the client can't tell the difference between the legitimate access point sponsored by the corporation and the bad guy's access point. So the client can't tell which one is real without stronger authentication mechanisms in place. And that's what allowed this man-in-the-middle attack to occur. So the bad guy stands up his own rogue access point. Now, this is an unauthorized piece of hardware in the network, and we should be searching for these on a regular basis and sorting them out and then reprimanding or perhaps some other form of penalizing the person who implemented this access point. This should be against company policy, and there should be punishment associated with standing up your own access point in the enterprise. So the bad guy stands up his own rogue access point, and he configures his service set identifier. Remember, that's the name of the wireless network. He sets that SSID to the same as the legitimate access point that the enterprise set up. So let's say the legitimate corporation is called Boboville, that's the SSID. The attacker will set that same SSID Boboville on his wireless access point. And now, if he can position his access point closer to the client's because his signal is stronger than the legitimate access point signal, the clients will preferentially associate with the rogue access point. And of course, the bad guy is going to say, yes, of course I'll let you authenticate and associate. Yes, you're the guy, because he wants that client to think he is the legitimate access point for Boboville. Now, at the same time, what the attacker is going to do is he will associate with the legitimate access point. And typically he'll do this by stealing a credential, and he'll pretend that he is the legitimate client associating with the legitimate access point. But again, he's not. He's the bad guy. And now what happens is the client thinks he is actually communicating with the legitimate access point, and the legitimate access point thinks he is communicating with the legitimate client, but everything is being channeled through that man in the middle, allowing him to violate the confidentiality. He can steal the secrets. It also allows him to violate the integrity. He can manipulate the data, and it also can allow him to violate the availability of the communications. He can simply choose not to forward the communications on. So the bad guy simply receives it from the client and pumps it up to the access point after he's viewed it and manipulated it at his discretion. And when the access point responds, the access point sends it back to the middleman, the attacker, and allows the attacker to view it and to compromise it however he cares to. And if he chooses to, he can forward it back onto the user thinking this is the legitimate response from the legitimate access point. So this is the rogue access point and the man in the middle, a relatively easy attack to accomplish in the wireless network. This is why we need to strengthen our security for wireless networks. These should be considered hazardous. As you notice in the diagram, there's a firewall isolating the access point from the resources on the corporate LAN. This should be a standard component of any wireless network implementation. We'll take a break at this point and move forward in the wireless networking lessons. In this lesson on wireless networks, we're going to review the baseline recommended security for wireless networks. Let's start with changing the default service set identifier. Typically, if the SSID is still set to the original default SSID, this is an indication of a non-configured wireless access point, which means security is at a bare minimum. So always change that SSID from the original to something new. And you should also at that same time set an administrator username and a strong password for the administrator account for that access point. Next, try to choose an uninteresting and unprovocative service set identifier. I've seen SSIDs that say, "Come hack me." Well, you know what? You're just challenging the bad guy. You're asking the bad guy to come break into your network. You don't want to set up Bobo's wine and tequila store, because now you're also identifying to perhaps the alcoholic type of attacker. This is a juicy target. Or Bobo's gold and diamond store. Well, man, there's a lot of valuables there. Maybe I can figure out how to defeat his security system physically and break in and steal all the gold and diamonds. So you want some unprovocative and uninteresting service set identifier in general. Now, if you're a hotspot, then of course you want your SSID to be broadcasted and you want it to be something interesting to bring people in. That's a different story. But from an enterprise level, you want this to be kind of generic and uninteresting. Turn off the SSID broadcast if you can. Again, if you're providing services to the public, like in a conference room in your office or some hotspot at Starbucks, then you need to leave your SSID broadcast on because you're trying to attract those clients. However, in the enterprise, all of those wireless client nodes should know the SSID. If not, make it part of the policy and part of the training. If you want to connect your device to our wireless, here's how you do it, but that's only for the trusted employees. If you can implement MAC address filtering. Now, I say that. The point is, the only way you can implement MAC address filtering is if there is a finite collection of nodes that you trust and you only want those nodes to be able to use your wireless network. In most cases, MAC address filtering isn't possible because I have to support too many different nodes. It might be a cell phone, it might be a laptop, it might be some pad device. They kind of come and they go, and I can't keep track of all the approved MAC addresses, so I can't keep this list updated. Next, if possible, implement WPA2, which includes the use of the Advanced Encryption Standard Encounter Mode and the use of cipher block changing message authentication code for data integrity validation. You want to implement enterprise authentication if possible. Now, home users don't have radius servers and directory services available typically, and as a result, they would use the personal level or home level of authentication and encryption. However, if you've got an enterprise class wireless network, you should have these resources available, and if not, you should get them going because you have greater losses potentially if a bad guy does break in. You need this stronger level of security. You want to implement mutual and multi-factor authentication for these wireless clients. In other words, not only do I need to prove to the client that he's associating with the correct network, I need him to prove to me that he's the right client. So that's called mutual authentication, where we authenticate each other. And then in addition, I might make him use his password along with rapidly changing password, one-time password, if you will, from a token device, for example. So multi-factor authentication is the use of two different authentication mechanisms, something you know, something you have, something you are. I might say a thumbprint and a password for multi-factor authentication. Now, another way we can help to secure our wireless environment is to not propagate our wireless signal any further than I need to cover. In other words, if I don't intend to support wireless clients in the parking lot, try to tune my signal, my wireless signal, so I'm not propagating a great deal of power into the parking lot. Now, this cell shaping is what it's called, is probably your weakest form of security because a bad guy with a good antenna can connect to your wireless network from hundreds of yards and maybe even miles and miles away. So this cell shaping is very weak. Basically, you're knocking down the dummies here once again. If they really have the intent to break into your wireless network, cell shaping probably isn't going to help you. But if I don't need to propagate a strong signal into the parking lot or the building next to me or the football field, then I can shape my cell to focus the energy where I do want coverage and minimize the energy where I don't want coverage. Always treat your wireless network and segments as hostile. Always isolate the access points from the corporate LAN through a firewall. Isolate them, separate them, and then filter that traffic heavily. And anything outside that firewall on the wireless segments should be considered bad guys, potentially. So I'll always treat them with the utmost scrutiny, stronger authentication, stronger encryption, etc., etc. And then finally, always require a VPN for data transmission. We talked about the use of a radius server and a policy that says the user is only allowed to send encrypted data. Now, what that says is he can authenticate using the 802.1x port-based authentication. Anybody can. And he can send data, but before he sends any real data, he must first establish an encrypted channel with a VPN server of our choosing, and it has to satisfy these encryption standards. So all data that the user is going to transmit over the wireless network must be encrypted with the VPN. And that would be another component of strong security for the wireless network. Now, moving forward, let's take a quick look at the structure or the architecture for the wireless network. Top left, we see the public internet, that very hostile, untrusted, wild, wild west environment for networking. And that's where all the bad guys live. And then we see what we call classically our demilitarized zone or our perimeter network, which hosts our public services. This would be our web server, email server, DNS server, FTP server, whatever else I want to expose to the public internet. I put them out there in that DMZ. And I also consider that area to be hostile, and I also consider it to be already compromised. And if you have that mindset about your DMZ, you understand what you should and should not put out there in your DMZ. Nothing valuable, because if you assume the bad guy already owns that space, you already realize you don't want to put anything of value out there. Now, back behind that DMZ, those two firewalls, we see the corporate LAN, and this is our more trusted computing environment. And we have the general corporate LAN, that's where the bulk of our resources live. But then you'll also notice I have two segments that are spawned off, accounting and R&D. These are where I have high-value information assets, and I want to protect them further, more staunchly, and limit access. And I'll do that with a controlling firewall, that security device that segregates but also joins these segments together. So now I've isolated those two high-value segments for accounting, all my financial data, and R&D, all my new inventions and stuff like this. I isolate them and control communications in and out of those segments very carefully. Now down below, this is the area of interest for wireless networking, we see another firewall, and only out there is where we put our access point. Don't ever put the access point on the corporate LAN directly, because you have to assume, because I can't physically see this guy, he doesn't have to physically be in my building, he might be a bad guy and I'll never know. So I'm going to treat everybody attached to my wireless networks as potentially a bad guy. And only if he authenticates properly using my strong authentication, and only if he follows all the rules of my policy, will I allow him to communicate through the firewall to the corporate LAN where I have my valuable resources. So as you can see, we consider the wireless segments as hostile as the internet. And with this, you have your head on straight about the security or lack thereof of your wireless networking environment. We'll take a break here and pick up where we left off. In this lesson, we're going to continue with a look at wireless networking, and we're going to explore the newer technologies called multiple input, multiple output technologies, as defined by 802.11n and the new draft specification called 802.11ac. Now, the point behind MIMO, this multiple input, multiple output, is to improve data rates and improve distances with your wireless networking capabilities. As you recall, with 802.11g and A, we had up to 54 megabits data rate. However, with 802.11n, we can operate up to about 600 megabits. That's 10 times the throughput of the A and G wireless networks. Now, how do we get this increased throughput? Well, we do this by using multiple transmitters and multiple receivers and multiple antenna in a single access point. And then each of these transmitter-receiver pairs can be used to communicate 48 or more data streams simultaneously. And this is how we increase this throughput. We also, using some very powerful circuitry called digital signal processors, can take advantage of what had earlier been a problem called multipathing, which was kind of interference. Now we can actually take advantage of that interference, that secondary reflected signal, and actually intelligently add that reflection, which prior was interference, and add it to the original signal intelligently and boost that original signal. So this multipathing capability and the multiple transmitters, receivers, and antenna help us improve this data rate. Another component of this is I can't put these antennas super close to one another, so I have to spread them out a little bit. And that's why we might see a wireless access point with multiple antenna and they're separated. This is referred to as spatial diversity. And this spatial diversity is a key component of this multipathing phenomenon that I described, which now is being used to our advantage on our data rates. Another component of this is I can use these multiple antenna that are spatially diverse and use phase shift steering and create what we call a phased array, tending to focus the energy in a specific direction to increase the distance of transmission in that direction. In other words, those waves recombine from those multiple antenna at some specific point way out there in the distance. And this is called a phased array and helps us improve the distances that we can transmit our wireless signals. As you recall, with 802.11, A, B, and G, we got to about 100 meters or so with our wireless networks. Well, today we can go more than 100 meters, hundreds of meters, and even miles or tens of miles with our wireless communications. A great deal of data throughput and distance associated with 802.11n MIMO. Now, 802.11n is where we are currently, and we are just moving into the newer 802.11ac. We'll cover that guy in a minute. Now, the 802.11n can utilize either the 2.4 gigahertz, that's the industrial, scientific, and medical frequency band, or it can use the unlicensed National Information Interchange band, the UNI band, up at 5 gigahertz. It's much less crowded up at 5 gigahertz. In other words, there's much less interference operating between 5 and 6 gigahertz as there is down in the ISM band, the 2.4 gigahertz. So we can take advantage of one or the other or both of those frequency spectrums in our 802.11n access points and clients. Of course, you have to understand what it is you're buying when you're buying that gear, and you're buying your network interface cards for the clients. You need to be sure that they're all either 2.4 or 5 or both sets of radios. You want them all to be kind of synchronized. So this 802.11n is forming the basis of our upcoming 4G cellular communications. Now, 4G, many people think their cell phones are already operating at 4G. That's a marketing lie. It's a fallacy, if you will. And they basically wanted to sell new hardware. There are improvements in 3G, so it's better than 3G, but it's nowhere near 4G. So they lobbied, petitioned, and eventually found their way to calling it 4G long-term evolution, LTE, and that's where we are today. It's an advancement over 3G, but it is nowhere near true 4G cellular. So when I refer to 4G, I'm talking about true 4G, not the LTE version that we currently are running in many of our cell phones today. But this will be a core component of that true 4G cellular, or at least that's the thinking today, that will use 802.11n wireless networking along with whatever state of evolution we are with WiMAX, another wireless technology, and we combine all these together with the 4G cellular, the actual cellular communications, and that's how we'll satisfy the 4G data demands and reliability demands that the standard requires. The new MIMO specification is called 802.11ac. It's still in draft version, so it hasn't been ratified yet. And as a result, it still may move around a great deal. As a matter of fact, there is so much new technology that's coming into this arena in this particular type of technology that it's really the wild, wild west. It's really a shooting match out there. And the spec, though, is targeting somewhere between 2 and 8 radio transmitters and receivers, and somewhere between 2 and 8 antenna. And again, spatially diverse antenna. It just doubles the hardware requirements or specifications for 802.11n, which of course is going to further improve the data rate and the distances potential from these wireless access points. We're looking at gigabits of data throughput. And again, still it hasn't been ratified. The standards haven't been ratified yet. But we are really seeing tremendous improvement in the data rates and the distances. The 802.11ac is going to be isolated to only that uniband, that 5 gigahertz to 6 gigahertz frequency spectrum, because it is so unpopulated in that spectrum. That spectrum is really only for wireless networking, whereas the ISM frequency band not only is being used for wireless networking, but other sorts of wireless communications. And as a result, there's a whole lot of traffic there. Now, moving forward, let's do a quick review of our cellular services. We originally had our first generation cellular, which was voice only, and these used telephones that were something akin to a boom box you'd carry around on your shoulder almost, big, heavy devices, and they were analog. Second generation went to a digital telephone, digital network, and had some basic communication services like caller ID, paging, and basic email. But it wasn't fast and it wasn't easy. Now, the third generation is where we got kind of a big change in technology. And this is where our cell phones were always connected. They were digital, and we had decent data communications. But it still wasn't like true laptop or pad device. There was some connectivity, basic connectivity maybe to the internet, but it wasn't great. Finally, we're at fourth generation, or not quite fourth generation, 4G long-term evolution. This is a nice improvement over 3G, but it's nowhere near the standard for 4G. So 4G LTE is our current state of technology. We're getting hundreds of megabits in most cases where we get good connectivity, but that's where this falls short, is the connectivity. 4G says that your connection over the 4G cellular network should be as reliable as if you were attached with a hard wire, a cable, and our cellular services are nowhere near that. In addition, it says every client associated to a cell will get 100 megabits uplink and 100 megabits downlink simultaneously. Well, our cellular services can't provide that as well. So we're nowhere near true 4G, and we're currently running on this 4G long-term evolution, kind of a marketing lie to the public. They think they're on 4G, but they're really not on 4G. The way we're going to get to true 4G, if we can get there in the foreseeable future, is by using something called alternate MAC layer, that's the data link layer, layer 2 of the OSI model, and physical layer, that's layer 1 of the OSI model. So we're going to use alternate technologies in layer 1 and 2 of the OSI model, in addition to the cellular services, and we combine all that together, and that's how we might get these high data rates and high reliability that is the requirement for the spec for 4G. In these next lessons, we're going to be looking at attacks on networks and information systems. There are two primary categories of attacks. The more common in the earlier days were more of the browsing attacks. These were not targeted attacks, they were opportunistic in nature. In other words, we're going to bump into as many nodes as we possibly can, and whatever nodes are vulnerable to my particular type of attack, those are the ones that I'm going to get, the victims that I'm going to be able to attack. It wasn't so targeted. It was more just kind of grazing. They called them machine gun, spray and pray, shotgun, drive-by attacks. Basically, we didn't know or care who we were attacking, we just attacked. And we bumped into everybody. Some people had their defenses up and I wasn't successful, and others didn't have their defenses up and I was able to accomplish what I wanted. So the common approach here was a virus or a worm or some script that I write and I put it on a website and it runs some processes on your computer if you download my script. And if you have your defenses up, the script won't run. But if you don't have your defenses up, like many non-sophisticated computer users might not know how to configure their defenses, then my script is going to run and I'm going to own your box. So these were the browsing attacks. And this is the way the bulk of attacks occurred all through history up until about 4 or 5 years ago, when some really good bad guys, and I don't mean good in a good sense, I mean they were talented bad guys, started formalizing their procedures, and they started targeting the more successful and profitable victims. So we might even refer to these as the newer family of these. The most sophisticated we've seen today is called the Advanced Persistent Threat, the APT. Here is where we will actually choose the victim. We'll select a target first, and then we'll recon that target. We'll study them. We'll anonymously nose around on their website. Now, there's an awful lot that, as an anonymous browser of a website, there's an awful lot of potential information that you can glean about the server itself, about the nature of the scripts that are running. Can I poison one of these scripts? About the infrastructure behind the web server. Because a lot of time the resources that a web server pushes down don't actually live on that web server. They has to reach back across the network and grab stuff. Well, if I can find those links, I now know more about your background infrastructure. So as passively as I can, I'm going to study and research and figure out who you are. And then over time, once I kind of exhaust those avenues, I'll become more and more visible as, hey, what is that guy doing out there? Anonymously, I'm a nobody. They don't even see me. But now that I might be probing your network a little bit, they'll say, hey, we just got scanned by somebody in Oshkosh. They might be able to recognize me. So this is recon. And the lower level is all passive. It's done through sniffing and browsing and using anonymous and publicly available information. Study the potential target. And then I'll get more and more active, and that's where I begin to risk some exposure. And my goal here is to first footprint the target environment. And that's kind of getting a general lay of the land to identify where there might be juicy targets. Is there a segment over this way and a segment over that way? And there's some resources back here. Once I get this footprinting done, this general lay of the land, I'll identify specific targets that I'm interested in. This is called fingerprinting. And I'll go interrogate that one specific server, for example, to try and identify its operating system, the applications it's running, the services it's running, the user accounts that might be there, things along these lines. And the more I can glean about that particular computer, server, if you will, the more I will understand where it might have vulnerabilities, because there is a database of known vulnerabilities, and many of these vulnerabilities still have not been repaired, patched, if you will. So if I can identify that you're running a particular version of Windows and SQL Server and you're running these 3 services, I might have 10 or 20 potential exploits that might attack vulnerabilities relative to those pieces of software that server is running. And so that's the fingerprinting now, where I'm studying a single device and I'm enumerating the details, the user accounts, the services, the applications, the protocols, the ports, the IP addresses, etc., that this one box is using. And I'm documenting this, so I'm building my profile of my potential victim. Through this fingerprinting and enumeration is where I can do my vulnerability assessment. How can I break in? Now that I understand how I can break into this one box, and I might have 20 exploits and 18 of them are already defended because you've patched or you've got a filter on your firewall or whatever, I might get one or two that work. And all it takes is one or two and you can break into a box and boom, that's the exploit. This is where I successfully compromise the box and I begin to take control of the box. I am now an unauthorized user on that target box. My goal here is to eventually raise my privilege level on that system to that of the administrator or the root. This is the top level of authority, and I can go anywhere and do approximately anything I want to on that box. So once I get into the box, I'll nose around a little bit, but I'll very soon try to escalate my privilege to some higher level where I can do what I want on the box. And as I get more and more control over the box by escalating my privilege level on the box, I'll also be covering my tracks. See, some of the tracks that I put down as I'm banging into this box with my exploits and trying to escalate my privilege level, some of these are going to leave marks that I can't hide yet. But once I become root or administrator on a box, depending on the operating system, now I can start to delete some of this stuff and I can cover my tracks. Also at this point, a good bad guy is now going to turn around and is going to harden this box. In other words, I'm going to fix all the vulnerabilities you didn't even know you had on the box. Why? Because I've worked hard to break into your box and make it my box, and I don't want another bad guy to take my box away from me. So I'm going to defend your box, which is now my box, from the bad guy who wants to take it away from both of us. So a good bad guy at this stage 6 where he's covering his tracks will also tend to shore up your defenses for you if you haven't done a good job. Now that I'm fully entrenched in this box, I can start to pillage. This is where I take whatever I want and I have my way with this box and I install whatever resources I want on it and I can steal whatever secrets I want off of it and I'll fully exploit this box and take everything I want off of this server, for example. And once I've taken everything I want off of this box, I now will use this box because it is in a trusted position in your computing environment. I will use your box as my attack point, and I'll pivot and attack deeper into your network using this system. So this is the nature of the targeted attacks. This is a full phase attack, and these are the components that would be included in what we call the new advanced persistent threat. The goal is eventually, over time, no hurry, very low profile, very low threat of being detected, fully compromise the box. Take everything you want from the box, and now use this box at your discretion, very often to penetrate deeper and steal more in the corporate environment, and the victim never knows that you were there. That's the goal of the advanced persistent threat. And what makes this so scary is this is now becoming more and more a common approach in a corporate world for corporate espionage. Also, there is new government-sponsored targeted attacks that will use this very low and slow and sophisticated, very difficult to detect type of attack. If I haven't scared you enough, maybe you'll come back for the next lesson. This lesson will cover the denial of service attack and the distributed denial of service attack. Now, the denial of service attack was one of the earliest types of attacks, and the goal of the denial of service attack is to eliminate the availability of some valuable IT resource. Maybe I'm corrupting your database and you can't get your data out of the database. Maybe I cause your server to crash so that you can't access your own server. Maybe I disable the network interface card on your web server and now your customers can't use your web server to buy through the e-commerce portion of the web server. So these are attacks that target the availability of information or networking services. And there's a whole family of them. These were the easy ones, relatively easy attacks, because in the early days, the network was designed and developed with the notion of how are we going to make this thing work? And it was all about making it work. And nobody really paid much attention to how will somebody use this network to screw things up. And that's where these denial of service attacks, relatively easy denial of service attacks, came into play. And that is because we were so focused on making it work, we never really paid attention to how do we defend the network from somebody who's trying to break the network. The original notion was, well, why would somebody do that? Well, they do. The bad guy simply wants to mess things up for the challenge, for the sport, for the game, or maybe for some financial benefit. Maybe he's your competition and he doesn't want you selling your product because if the customers can't get to your website, they might come to his website and buy his product. Things along these lines. So a whole family of these. The first one is called the Sin Flood. Took advantage of the TCP three-way handshake, and it built a half a session and then never completed the session. Only it would build half a session 1,000,000 times over and flood the target system with so many TCP sessions that were incomplete, incomplete, if you will, that the server can no longer handle a legitimate inbound request for a TCP session. The teardrop and the smurf, the ping of death, and the land attack are all attacks that are designed using legitimate protocols, but misusing the legitimate protocol so that the target system can no longer function correctly and handle legitimate requests for service. And so that's a denial of service attack. Anytime you can break their box or their access to the data, you have denied them that service. And as a result, they are going to lose money. And for some reason, that must be to your benefit since you're the bad guy. Now, the distributed denial of service attack takes some advantage of some of those features from time to time, but really is a little bit larger scale. And here's the way this works. Over time, a bad guy will compromise many systems using the opportunistic browsing types of attacks. In other words, he will populate the internet, if you will, with, let's say, 100,000 compromised systems. Over time, over a 6-month or even a year or even longer period, he'll implant his unknown virus on these boxes. And because the payload hasn't fired yet, it hasn't done anything yet. These boxes aren't doing anything except monitoring a communications channel, which I'll describe in just a minute. So, over time, we compromise many boxes, as many as we can. Now, these boxes are eventually going to be referred to as zombies, and they may also be referred to as bots, because my virus that I've infected these computers with is monitoring an IRC communications channel. Typically, it's using the Internet Real-Time Chat, IRC, and that's because these are anonymous communications. So I've compromised that box over there, and now I've programmed that box to every hour go look at this chat room, and if he sees over the last hour that somebody has input the command or the sentence, Bobo was here, he's looking for that phrase. If he sees that phrase, that triggers some action on his part. So that's what my Trojan, that's what my virus is doing on that compromised box. And so I'll, over time, increase these number of compromised boxes, building my army of zombies or my botnet. Those two terms are approximately synonymous. And these are compromised systems that are monitoring this anonymous communications channel. And as I build my army bigger and bigger and bigger, I might sell it, or I might use it to really focus an attack on some other corporation that I have some grievance with. So now I'm getting more and more powerful as I increase the number of zombies or bots in my army of zombies or botnet. Now, when I'm ready to pull the trigger and actually evoke the attack, what I'm going to do is I'm going to take another compromised box, and this one isn't going to be one of my zombies. This one I'm going to call a handler. And this is a compromised box who is looking at a different chat room. And this time he's not looking for Bobo was here. He's looking for Lulu was here, for example. And so I, the true attacker, will log on to the IRC chat room and say Lulu was here. And my handlers, maybe 100 of them, I'll have 100 handlers, are going to be monitoring this chat room every hour. and they'll see that sentence, Lulu was here, and they will turn around and communicate using the other chat room and post the message, Bobo was here. And the compromise boxes, the zombies, hundreds, thousands, tens of thousands or more compromise box, the zombies or bots, will see that command, Bobo was here, and they will turn around and execute the attack on whoever the victim is. And sometimes those communications will include enough information to identify the victim and the type of attack on the victim, the timing of the attack, things along these lines. And other times that will be embedded in the virus itself. I'll already know who the target is and the nature of the attack. And I just pull the trigger using these commands through these IRC chat rooms because they allow me layers of anonymity. And some of these attacks include the Tribal Flood, Trinu, and MyDoom. These are some of the more famous distributed denial of service attacks. And there are continued variants of these types of attacks, but very often these are denial of service attacks on a singled out target, a well-focused, well-targeted attack, well-coordinated, and through layers of anonymous chat rooms, I make it very difficult for the attack to be traced back to me, the true attacker. So this has been the denial of service attack and the distributed denial of service attack. Let's continue our lessons now with a review of the different types of information theft. This is where the bad guy breaks in and steals your information. The first and easiest one is referred to as sniffing, and this is using what might be called a protocol analyzer, packet analyzer, a sniffer. These are applications or devices that we can attach to the network, whether it's wired or wireless, and we simply capture the information that's flowing back and forth across this network. If there are encrypted channels, then anything that's encrypted, of course, while I can capture the packet, the payload is going to be gibberish to me and it's unintelligible, and I don't get any usable data out of it unless, of course, I take the time and crack the encryption. Now, this can take a very long time. Today's cryptology is very, very sophisticated, and if they're using good crypto, it might take me years, decades, centuries, millennium to break into their ciphertext. So very often, if it's encrypted, that encryption is strong enough that there's almost no point in trying to break into it. So this is a relatively anonymous form of eavesdropping, and it's a very easy way to steal information. If the network is wireless, or if it's using unshielded twisted pair, and these are the two most common forms of network communications today, these types of technologies emanate the data signal into the air. So as you're sending packets through that wireless network or through that Ethernet network, there are electromagnetic waves in the airspace that a good bad guy can pick up and steal those data streams. So this is emanations detection. Now, the way to defend against emanations detections is by use of shielding, maybe a Faraday cage, or you can also populate the environment with something called white noise. In other words, I'm kind of jamming the signal. I populate the environment with radio frequency energy that is a higher level, so high that you can't read my emanation signals because they are substantially weaker. And in all that noise, you can't identify the true data from the noise. Now, the man-in-the-middle attack is where the bad guy spoofs both a legitimate server or service and also then spoofs a legitimate user. And the client thinks that the bad guy, the man in the middle, is the legitimate service, so he's communicating back and forth freely with what he thinks to be is the legitimate service. Meanwhile, that bad guy, man in the middle, is going to turn around and pretend to be that legitimate user to the legitimate service. And as a result, he is now the man in the middle. And he is able to intercept 100% of the communications between the true client and the true legitimate service. And he's able to compromise the confidentiality, the integrity, or the availability of that information as it flows through him in the middle. Now, the bad guy can also hijack a network or a website or something along these lines. Let's talk about this. If I can break into the routing system of a network, I can cause the routing system to send all of their traffic through my segment where I'm perhaps going to run a sniffer. This way I can steal any data that isn't encrypted. And I might hijack your website. In other words, I pretend to be your website and I poison the DNS so that when a client thinks he's going to boboville.com, he's really going to badguy.com, but I've made it look like it's at boboville.com. And now the bad guy doesn't know that I'm sending down my malicious software to his browser every time he hits my website. So this would be a form of hijacking. ARP cache poisoning poisons the layer 2 MAC address information. That's what ARP does. It does IP address to MAC address resolution, and then the client will cache that mapping in RAM for some period of time. Typically it's 10 to 12 minutes. Now, if I can inject my mapping of the legitimate IP address, only the bad guy MAC address, into that ARP cache, now the legitimate client thinks he's sending his data to the legitimate server, but really he's sending it to me, the bad guy. This is one way to invoke this man-in-the-middle attack. Same with DNS poisoning and route poisoning. These also allow for either man-in-the-middle or hijacking attacks. So DNS poisoning is where I break into a DNS server that stores the mappings of friendly names, fully qualified domain names like www.boboville.com, and it has its legitimate IP address posted there in that mapping. But if I can break into the DNS server, I can put my bad guy IP address into that mapping. So now when you think you're going to boboville.com, you're actually coming to badguy.com and allowing me to send you whatever it is I feel like sending you, or I pretend to be the legitimate site and I trick you into sending me your username and password so I can turn around and go clear out your account or steal your credit card information, whatever. Traffic analysis is not actual theft of data other than I can identify trends. I can tell when something is happening. If I know about your business because of the reconnaissance that I've already implemented on your business, I might be able to tell when you're sending out your payroll data, for example, or you're processing your credit cards. I can tell when you're processing your credit cards because of the nature of the traffic. Now I can go to the processor and break into his network today because I know he's got all those new credit card numbers. So through traffic analysis, not the actual analysis of the information, the detailed information that the traffic contains, but just the increase of some type of traffic or the decrease or the nature of the traffic as it changes, I can glean conclusions about the nature of what's happening. And this might trigger me with some intelligence to more accurately, more effectively attack and compromise your environment. Now, we talked about the distributed denial of service attack that uses IRC, Internet Real-Time Chat, instant messaging in chat rooms, and I can use these tools to help to steal information. Most of the time, these are anonymous. Most of the time, these don't have encryption, and many times, people will put all sorts of highly sensitive information in these chat rooms. Plus, I can use these chat rooms to my benefit to help me orchestrate attacks. So the very anonymous and almost always clear text communications through instant messaging and chat rooms allow me to steal that information and allow me a free and anonymous channel to effectively communicate and help coordinate my attacks. Another form of information theft is through the use of something called a backdoor or a maintenance hook. Now, when a software developer is writing his program, there's a fair amount of trial and error. He'll write his code and then he has to go test it. But he doesn't want to have to go all the way back through the application to test it, so he'll build this little entryway, this little maintenance hook it's called. It's a doorway into his program without going through all the authentication and authorization challenges that you bump into when you first log into an application. He wants to jump right into the program right before this piece that he's been working on because he just wants to test this piece and kind of debug it and work it out. So very often during development, the developer will legitimately have a use for this maintenance hook. This is a backdoor. It's unauthenticated avenue into the application for testing purposes, and it's legitimate testing purposes. That's great. The problem is these developers will very often intentionally or unintentionally leave these maintenance hooks in the code because they didn't want to take the time, they forgot, or they know there's still a problem there and they're going to have to go clean it up later. So I'm just going to leave that maintenance hook right there because I know I have to go work on this again later. Now, when the bad guys can identify these maintenance hooks in the application, This is their easy backdoor. They now know how to step into the application, bypassing all the legitimate authentication and authorization mechanisms that are in place on the front end of the application. Also, if a bad guy can compromise a system, he very often will inject Trojaned applications that include the backdoor so that he can come into this system anytime he cares to, over and over and over again. So the bad guys will very often inject these backdoors, usually through a Trojan horse type of application, and be able to bypass authentication and authorization mechanisms that might already be in place on the box. And finally, this last one isn't really a high technique. This is a low-tech attack at stealing information, and this is called dumpster diving. And the notion here is people don't ever really pay that much attention to what it is they're throwing away and just how sensitive that stuff is that they're throwing away. And once you put a piece of information or a hard drive or a floppy disk or a CD-ROM in the trash, and that trash gets put out for collection, in most cases, it is declared that there is no ownership of that item. In other words, you've given up ownership of that item, and nobody owns it, which means it's not exactly against the law for a bad guy to come take it. It's not theft anymore. You've given it away, in essence. So we have to be very careful about destroying anything that contains any sensitive information to avoid the threat of dumpster divers being able to compromise and steal value from your enterprise. This is also appropriate for home users as well. Be concerned about what you throw in your own personal trash, because somebody might be looking through your garbage and stealing your identity or other valuable components of your worth and your value. We'll take a pause here and pick up shortly. In this lesson, we're going to continue on with different types of attacks. This particular attack is referred to as the advanced persistent threat. Now, this is a relatively new type of attack, and it is very often corporate-sponsored or perhaps even government-sponsored. It is highly targeted, it is highly sophisticated, it's called low and slow, with a very low potential for being detected. The goal is break in, doesn't matter how long it takes, break in, take what you want, and go away, and they'll never even know we were here. That's the goal. So it uses a very slow and stealthy approach, a whole lot of reconnaissance, study the target, identify vulnerabilities, and the moment you think maybe they've noticed something, you completely obliterate any trace of that particular action, and you come in at a different angle from a different attack vector. And so the goal is, we don't want them to know that we've ever been here. Don't let them know that you broke in, that you're breaking in. Not only breaking in, I don't want them to know when I've stolen their stuff, and I don't want them to know when I've cleaned up and left their place. They should never even know that I've been here. So this is highly targeted. It is one of the scariest types of attacks. We're seeing it happen more and more often. Some examples are the Stuxnet, Dooku, and Flame attacks, all in kind of the same family of attack, and these all fit into this advanced persistent threat type of attack, where you might study your target for a year before you ever start to inject any sort of malware. So it's a highly skilled attacker, slow, determined, stealthy. This is where we will use all phases of the attack, and that would be the recon, the footprinting, the fingerprinting, the enumeration, the exploit and compromise phase, the escalation of privilege, the covering of tracks, the hardening of the asset to defend your new asset so some other bad guy doesn't steal it, the pillaging of the resources, and eventually the pivoting and attacking deeper into the enterprise. Now, that pivot and attack is an option here because the goal is we don't ever want the victim to know that we were there. As compared to earlier attacks were not targeted. They were, let's grab the low-hanging fruit. Let's find the easy targets and we'll take them. They didn't know or care who those targets were or what they were going to get. They just figured if I can bump into 1 million boxes, I might get 1,000 compromised boxes. And you know what? I'll make some benefit from those 1,000 boxes. Well, that's not the advanced persistent threat. That's the way early attacks worked. Today, the attacks are much more focused, much more stealthy, much more talented and skilled, and they are corporate or government sponsored with massive amounts of resources. Another form of attack or justification for attacks called this hacktivist. Now, this is somebody who hacks into a network or an enterprise just so they can draw attention to their cause. It might be about cruelty to animals. It might be about some sort of degradation of the environment or something along these lines. So they try to break into an enterprise or a network so that they can get publicity. They might be able to stop some action like the injuring of animals or the further fracking of the surrounding terrain. The hacktivist wants attention, whereas the guy who's committing the advanced persistent threat does not want any attention. He's on the complete opposite end of the spectrum from the hacktivist. Let's move forward and we'll look at cell phones, threats from cell phones. Now, in the early days, we had problems where a bad guy would get your code off of your cell phone and he would clone that same authentication code into his cell phone, and now he's using your minutes. Because the cellular company, the carrier service that you're paying, can't tell the difference between your telephone and his telephone. To them, they're both legitimately your telephone, and you're going to get billed for his minutes. So cloning was one of the early threats to cellular service. In the early days in cellular, that authorization code was sent in clear text. So a bad guy could simply set his recorder up in some city park, sit there and spend the nice day feeding the squirrels and soaking up the sunshine. Meanwhile, he's collecting the cell phone authentication codes, and then we'll go home and program his cell phones with those codes, and he'll be using your minutes, not his minutes. When it was recognized that this cloning was occurring, the cellular companies effectively started encrypting these authentication codes. So that defeated this particular attack. Oh, but wait a second. The bad guy doesn't need to know a specific authentication code. He needs any successful authentication code. And each cellular customer has their own legitimate, authentic, usable authentication code. So he only has to find one out of, 100 million or so authentication codes. In other words, there are many, many, many codes that he could guess, and this is a trial and error approach. He'll guess at these authentication codes, test, and if it doesn't work, he'll guess the next one, he'll guess the next one. This is called tumbling. So all he has to do is find one that works, and he doesn't care if it's yours or somebody else's code. As long as he can find one that works, he'll tumble on and tumble on and tumble on and tumble on until he finds one that works. Boom, he now is using your minutes. There's another threat called the gap in the WAP. WAP is Wireless Authentication Protocol. And this is a security protocol used by the cellular services. And basically what this says is, I'm encrypting your communications from your cell phone to the cellular tower and to the earth station at the foot of that cellular tower. And at the foot of that cellular tower is this earth station that has to decrypt this WAP encrypted communication. And it then has to convert that into the appropriate encryption for the internet or whatever network you're communicating with. So we have a server at the foot of some cell tower that has clear text communications. And if some bad guy can break into this location, and how many cell towers are there? A lot. So how many locations are there where we have clear text information? A lot. And how secure are these? Well, that's a question mark. So we have this vulnerability as well. Now, a legitimate client can take their cell phone, plug it into their computer, and use the cellular connection to connect to the internet. Now, your desktop computer in the enterprise, instead of all communications to the internet go out through my firewall that I can monitor and control and regulate, now we have a parallel path out to the internet that I, from the corporate position, can't monitor. I don't even know it's occurring, and I can't even monitor it because it's going through a user's cellular telephone that's been tethered. So this is a breach of our security because we're bypassing network security. wireless hotspots, Wi-Fi hotspots, like at Starbucks and other places where they want you to plunk down and spend the day because you'll order 16 cups of coffee and 14 carrot cakes while you're sitting there using their free internet at their hotspot. These are also very dangerous areas because very often they have either no security or very weak security. And as a result, the bad guy will plunk down there and he's just going to sniff all the traffic. And using a sniffer, a wireless sniffer, he can read every data packet that you send and receive in these hotspots if the security isn't strong. The cell phone can also store a whole lot of data. My cell phone has about, I think, 48 gigabytes of storage. That's a whole lot of data. So I can connect my cell phone to my computer at the office and download anything I want onto my cell phone, and you guys will never even know that I'm stealing all your secrets. The cell phone also has a camera, so in high security environments, I might be able to sneak my camera into your environment and take photographs that are otherwise unauthorized. And you're looking for a camera, well, my cell phone today has this camera built in. It also has an audio recorder, good for eavesdropping, and very often, legitimate users will have data on their cell phone that is sensitive, and these cell phones are lost and stolen on a regular basis. So these are ways that data can be stolen through the cell phone, and in this case, it isn't a willful attempt to steal data from the company. You put data on there legitimately with a legitimate need, but now you lost your cell phone and some bad guy finds it and now has access to that sensitive information. So this has been a lesson on threats to networks, and we'll wrap up in the next lesson. This concludes our lessons on network technology and security. As you recall, we reviewed the OSI model, the TCP/IP suite of protocols. We looked at network transmission media and transmission technologies. We looked at network infrastructure components, including the personal area networks, local area networks, metropolitan area networks, wide area networks, and then some. We looked at wireless networking technologies, and then we looked at attacks on networks. If you want to dig deeper into these topics, here are some internet-based resources that you can use to study these topics a little further. Feel free to pause the presentation if you're going to go explore some of these or you want to write some of these URLs down. In order to qualify how well you've learned from these series of lessons, please answer these following questions. The answers are presented on the next slide, so again, what I ask you to do is just pause the video at this point and answer these questions, and then proceed to the next slide for the answers. So here are the answers for the preceding questions. The types of media that is used for networks from weakest emanation security to strongest emanation security are wireless, unshielded twisted pair, shielded twisted pair, coax, and then finally fiber optics being the most secure. Remember, fiber optics use photons, not electrons, and photons don't emanate, whereas electrons do. The other technologies use electron flow and therefore have some level of emanations, resulting in emanation security threats. The second question deals with the 4 different types of transmissions on a network. We have unicast, that's one-to-one. We have multicast, that's one-to-many. Remember, the multicast, they have to opt in to the multicast transmission from one source to many clients, and it uses the Internet Group Management Protocol. We have a broadcast, that is from one to all the nodes within a certain range. And what is that range? Well, it's defined by the broadcast domain. Typically, the router is the boundary for the broadcast domain, and bridges and switches forward all broadcasts. And then the last one is one that hasn't really gotten much use yet, but we might see it happening more and more as we evolve into IP version 6, and that's called the Anycast. Now, the Anycast is where I would assign a single IP address, the same IP address, to all the nodes that provide this one service. For example, all my DNS servers will have the IP address 10.10.10.1. And now we'll configure all the clients to go to 10.10.10.1 for DNS resolution. This is a one-to-one of many, because I can assign this same DNS IP address to many DNS servers, and you will send your query to that one IP address, but the nearest DNS server to you will be the one that your transmission is sent to, and you will receive the response back from. So this is one to one of many, the Anycast. The next one deals with firewalls. What are the 5 generations of firewalls? The first one was the packet filtering firewall. This was a router that had an application added to it that did filtering based on IP addresses and on port numbers. Now, this is a layer 3 device, and it was either wide open or all the way closed. There was no middle ground. There were no conditions other than red light or green light for that IP address and port combination. Second generation was called the proxy firewall. We had a circuit level and an application layer proxy firewall. This guy broke the connection between the client and the server. To the client, the proxy firewall resembled the entire internet. And to the internet, the proxy firewall represented all the clients that proxy server was responsible for. It could include user authentication, group authentication, all the services of the packet filtering firewall. It could do deep inspection if we were application layer and actually rebuild the content and provide content filtering, etc., etc. So the proxy firewall was very intelligent, but also very slow. Third generation was the stateful firewall. This said that all inbound requests are denied, except those inbound requests that I can find a stateful request that we submitted prior. So all inbound responses will only be allowed through if we asked for it. Anything unsolicited, deny. So this was our third generation. Now, the fourth generation packet filtering firewall is the combination of the stateful firewall and the packet filtering firewall. And this is really what a firewall needs to be at its minimum. We might add some of the intelligence of the proxy firewall on top of this. But basically, the dynamic packet filtering firewall, fourth generation firewall, virtually all of our firewalls today are that type of firewall and may include proxy capabilities as well. The fifth generation firewall was the kernel proxy. This guy doesn't exactly exist today. The kernel proxy, the notion was that if we could put this application that did the filtering, that is in essence, the firewall, if we could put that software in the kernel of the appliance, then it must be faster and stronger. The kicker, though, was now you've got all that dirty stuff coming back off the internet, all that dangerous malware and stuff coming back in that I have to bring down into the kernel and examine it before I can make a decision on it. This is too much dangerous stuff, too close to the heart of the device. And so the conclusion was this wasn't terribly safe or smart. So they pushed the bulk of this back up into the user mode and away from the kernel mode. And now I have an extra layer of security between that dangerous stuff that I'm filtering and the actual kernel of the operating system for the appliance. So the kernel proxy doesn't exactly exist today in that true original form. There might be some components of the firewall that live in the kernel, but the bulk of it is back up in user mode, not down in the kernel mode of the device. Question 4 dealt with secure channels or VPNs, and we have the secure shell, the point-to-point tunneling protocol, IP security. Remember, IP version 4 does not have any native security built into it. And when they realized there's a need for security at layer 3, they had to invent a new protocol called IPsec to implement that authentication, integrity validation, and security encryption for IP traffic. We have layer 2 tunneling protocol. This guy does not provide any form of encryption, but does encapsulate whatever you're transmitting in a layer 2 frame. So it is usable over all layer 2 wide area networks like ATM, frame relay, X.25. The next one is a very heavily used protocol today on the internet. It's a pretty good protocol, still quite strong and evolving. And this is Secure Sockets Layer and Transport Layer Security, SSL and TLS. The latest version of SSL is Transport Layer Security. They were slightly different than the early days, but the new version of SSL is TLS. We have SSTP, that's the Secure Sockets Transport Protocol. This is a VPN technology using SSL. And finally, question 5 dealt with wireless security. The original wireless security implemented in 802.11 was called WEP, Wired Equivalent Privacy. And then when they realized how flawed WEP was, they chartered a new task group and came up with 802.11i that included Wi-Fi protected access, a short-term transitionary security improvement over WEP, and the eventual, this is where we need to be today, WPA2, Wi-Fi Protected Access version 2. Now that is also called the Robust Secure Network, or RSN. And this completes our course on network technology and security.